48 years ago, the cosmos broke its silence. From the direction of Sagittarius came a solitary cry, a radio transmission that lingered for 72 seconds before vanishing into nothingness. Astronomers called it the wow signal, a fleeting whisper with no echo, a mystery suspended in space. Now, from that very same corner of the sky, another enigma arrives, an interstellar traveler known as 3I Atlas. Its chemistry resists explanation, its timing challenges belief, and together these puzzles align like scattered breadcrumbs across the dark. Could they be random coincidences, or signs stitched into the fabric of the universe itself? Perhaps, for the first time, humanity stands on the threshold of contact with intelligence beyond Earth. Two mysteries, one constellation, separated by nearly half a century, yet now their echoes seem to converge across time. In the year 1977, an enormous radio telescope in Ohio caught a sound the universe was never supposed to make, a broadcast so crisp, so deliberate, that it seemed to leap out from the static with the unmistakable cadence of intent. It lasted exactly 72 seconds, and then it was gone, evaporating into silence as abruptly as it appeared. The astronomer on duty, Jerry Eman, circled the numbers on the computer printout and scrawled a single word in red ink: wow. That exclamation became the name of the most tantalizing radio signal ever detected, one that seemed to point directly towards Sagittarius, the crowded heart of our galaxy. For decades it stood as a whisper from the unknown, a voice without a speaker, a mystery unsolved. Now, in the year 2025, the sky has spoken again from that very same patch of darkness. This time, however, it is not intangible radio waves flickering across a readout screen, but something with mass, volume, and presence, a celestial intruder plunging through our solar system on a path that does not belong. Astronomers call it 3I Atlas, the third confirmed interstellar visitor humanity has ever seen. It is no quiet signal this time, but a piece of matter hurtling across the void, carrying within it the fingerprints of alien chemistry and the secrets of an unknown birthplace. Like the wow signal before it, it comes from Sagittarius, and that shared return address demands our attention. Coincidence is one of science's most delicate words. In a universe of 2 trillion galaxies, each packed with hundreds of billions of stars, chance encounters happen all the time. Yet what are the odds that two of the strangest anomalies in modern astronomy would point back to the very same region of sky? Sagittarius is no ordinary constellation. When we look in that direction, we peer into the very core of the Milky Way, where gravity churns in the form of Sagittarius A star, a supermassive black hole 4 million times the mass of the Sunday. This is the Times Square of our galaxy, crowded, noisy, and unrelentingly energetic. Radio waves roar here in overlapping streams, a flood of signals from stars, pulsars, and clouds of ionized gas. It is at once the most obvious place to search for evidence of other civilizations, and the most maddeningly complicated place to separate voice from static. Yet the coincidence grows sharper when we recall the frequency of the original wow signal. At 1,420 MHz, it sat in a unique, almost sacred band of the spectrum that scientists call the waterhole. On one side lies the emission line of neutral hydrogen, on the other the signature of hydroxyl molecules. Together, they form the chemical basis of water, the prerequisite of life as we know it. For decades, researchers have argued that this is the frequency any advanced civilization would choose for interstellar conversation. It is quiet compared to the surrounding static, a natural resting place for radio, and its significance is woven into the very physics of the cosmos. The hydrogen line, at 1,420.4 MHz, is immutable, universal, a constant every radio-capable species would recognize. To transmit at that frequency is to dial the universe's most obvious number. The story, however, does not remain anchored in the 1970s. On the 1st of July, 2025, the Atlas survey system, scanning the skies from the clear desert air of Chile's Atacama, spotted something extraordinary. Against the familiar ballet of asteroids and comets that orbit in the sun's embrace, there moved an object with a different rhythm altogether. Its path was not an ellipse, not a circle, not any of the closed loops that mark a solar system body. Instead, its trajectory was hyperbolic, an open-ended arc carved by gravity but never captured by it. In the mathematics of celestial mechanics, such an orbit bears a single, unmistakable signature. This object was born elsewhere. Its eccentricity was greater than 1, the threshold that defines interstellar origin. It had not been shaken loose from the Oort cloud or strayed too far from the asteroid belt. It came from the deep between stars, and only the sun's pull has bent its voyage into a temporary detour. This alone would make 3I Atlas remarkable, but it is the context that sharpens the enigma. The first interstellar visitor, Oumuamua, rushed through in the year 2017, its elongated shape and strange acceleration provoking endless debate before it disappeared beyond our reach. 2 years later, Comet Borisov gave us another chance, but again only briefly, a bright blur soon gone. Both came and went with too little time for thorough study. 3I Atlas is different. Its approach grants us months, perhaps more, of observation, a luxury we have never had before. The James Webb Space Telescope now examines its spectrum in infrared. The Hubble Space Telescope constrains its size, rotation, and activity. From mountaintops around the world, ground-based observatories track the glow of its coma and the spray of its tail as sunlight liberates ices from its surface. For the first time in history, humanity can perform a slow-motion autopsy on matter, forged around an alien Sunday. And yet, as the data pours in, strangeness multiplies. Spectroscopic measurements reveal that its vapors are dominated by carbon dioxide, with a ratio to water near 8:1. By contrast, comets in our own system typically show the opposite balance. Stranger still, emission lines of nickel shimmer in its spectrum without the iron that almost always accompanies it, breaking the expected companionship of those metals. Observations suggest it is small, perhaps no more than 5.5 kilometers across. Yet it produces dust and gas with an intensity that dwarfs comets of comparable size. Some astronomers call it overperforming, as if it obeys rules written somewhere else. Skepticism is essential here. The history of astronomy is littered with puzzles that once seemed alien. Pulsars were briefly thought to be lighthouses built by extraterrestrials. Fast radio bursts carried similar intrigue before natural explanations emerged. Extraordinary claims demand extraordinary evidence, and the sober discipline of science insists we tread carefully. Perhaps the carbon dioxide is a quirk of its birthplace, the nickel anomaly, a matter of measurement. Perhaps coincidence really is all this island, and yet the symmetry is difficult to ignore. A signal from Sagittarius, sharp and singular, lingering just long enough to make us wonder. An interstellar body, decades later, arriving from the same direction, anomalous in ways that prod our imaginations. What if these are not isolated events? What if the wow signal was the opening note, and 3I Atlas the reply? For the first time, humanity confronts the possibility that coincidence might be carrying a message. Whether it is cosmic chance or something more deliberate, the mystery beckons us deeper, asking us to listen, to watch, and to wonder. We will approach the data with careful is separating what is firmly measured from what is speculative, allowing evidence to shape our understanding rather than wishful thinking. The path ahead invites us to revisit the history of both enigmas, to sift through the most recent analyses, and to weigh interpretations that range from ordinary astrophysical quirks to possibilities that could transform our sense of the universe. The wow signal and 3. Atlas may in the end share nothing more than our human tendency to link patterns in noise, two isolated mysteries bound by coincidence rather than causation. Yet even that convergence holds profound value. It offers a rare perspective, a mirror in which to see how we stand within a cosmos that surprises us, humbles us, and constantly reminds us how much remains unknown about the galactic neighborhood we inhabit. As 3I Atlas drifts closer, its path will bring it near Mars in early October, before swinging around the Sun and beginning its long retreat into interstellar darkness. For now, we have a fleeting chance to watch, to listen, and to wonder. In a universe where two riddles from the same sky cross our doorstep, possibility itself expands. On the 15th of August, in the year 1977, while most of America lay asleep beneath the summer night, a lonely sentinel in Ohio was listening to the sky. The Big Ear radio telescope did not resemble the iconic gleaming dishes that dominate our imagination. Instead, it was an enormous metal trough carved into the countryside, stretching nearly the length of 3 football fields. Its design was simple yet ingenious, a fixed reflector that used Earth's rotation as its clockwork engine, sweeping its gaze across the heavens one strip of sky at a time. That mechanical rhythm came with a limitation. Each star field was granted a single glance of 72 seconds, no more, no less. Only when the Earth had turned a full day later could the telescope look again. That night, as the constellation Sagittarius slid across its beam, the silence was broken. The receivers registered something wholly alien to their archives. A narrow band signal centered precisely at 1420.455 MHz, climbing in intensity as the sky moved, then fading away with mathematical perfection. To the engineers, this profile was unmistakable. It was exactly what an authentic astronomical transmission should look like, traced cleanly by the telescope's movement. Yet what truly stunned them was its strength. Reanalyses suggest its peak brightness may have reached 250 Janskis, some 30 times louder than the background hiss of the galaxy. In the language of radio astronomy, this was not a whisper. This was a shout hurled across the void. Days later, volunteer astronomer Jerry Eman sat before the computer printouts, stacks of numbers and letters generated by Big Ear's primitive processors. Each character represented the strength of incoming radio noise, most lines filled with the droning monotony of ones and twos. Then, his ears froze. There, in the quiet stream, rose an impossible sequence: 6 E U J 5. The letters spiked in symmetry, rising and falling in a neat arc, the unmistakable fingerprint of a point source passing through the beam. Stunned, Eamon seized a red pen, circled the anomaly, and in the margin scribbled a single exclamation. Wow! That hurried scrawl would become the immortal name of the most intriguing signal ever detected in the search for extraterrestrial intelligence. Everything about it fit the dream that SETI scientists had whispered about for decades. Its narrow-band nature hinted at artificial origin, for nature rarely carves such precise frequencies. Its rise and fall matched a fixed source in the sky, not the erratic behavior of satellites or interference, and most arresting of all, it rested almost exactly on the hydrogen line, the 21-centimeter wavelength that many believed would serve as the universal beacon of intelligent life. To send a message there would be to write across the very physics of the universe, a cosmic frequency every advanced civilization might recognize. Big Ear's peculiar design added another layer to the puzzle. Its two feed horns observed adjacent strips of sky, meaning any true celestial source should appear twice, separated by roughly 3 minutes. Yet the WOW signal appeared in only one beam. Its exact position was left uncertain, a gap in the record that would frustrate follow-up efforts for decades. The team at Ohio State University understood at once that they had stumbled upon something extraordinary. Within days, other observatories were directed towards Sagittarius. Telescopes waited, scanning for the voice to return. Nothing came. The silence was deafening. What had flared for those 72 seconds seemed to vanish forever, leaving behind only that fragile printout and the question of what had spoken. Thus began one of the longest and most determined follow-ups in SETI's history. Over the years, instruments from the Very Large Array in New Mexico to the Great Dish at Arecibo in Puerto Rico, from parks in Australia to smaller antennas scattered across continents, all turned their ears to the sky where Big Ear had heard its cry. Some listened continuously, others intermittently. All returned the same verdict: silence. The WOW signal remained a singular apparition, a mystery without an encore. Its one-time nature posed a philosophical dilemma as much as a scientific one. How does one prove the reality of something that refuses to repeat? How do you distinguish an alien voice from an unknown natural quirk when you have only one note in the symphony? The signal became a parable for what philosophers call the problem of induction, attempting to generalize from a single, unrepeatable observation. As time passed, explanations proliferated. Some suggested exotic astrophysical phenomena, neutron stars twisting their magnetic fields into rare alignments, or interstellar hydrogen clouds lit by distant cataclysms. Others conjured stranger visions, black holes interacting with unseen companions, or collisions in deep space producing brief, sharp flares. In the year 2012, astronomer Antonio Paris offered a more terrestrial hypothesis. He proposed that comets, surrounded by vast hydrogen clouds, might have been the culprits. Two comets in particular, numbered 266P Christensen and 335P Gibbs, had passed near the region around 1977. Could their hydrogen tails, bathed in sunlight, have created the narrowband emission at the hydrogen line? The reaction from the SETI community was swift and skeptical. Veterans of Big Ear pointed out that comets drift across the sky, while the WOW signal seemed fixed in place. No comet tail should have generated the astonishing intensity measured, nor the razor-thin bandwidth. Perhaps most damning of all, decades of radio astronomy had failed to find such emissions from any other comet. The hypothesis, while creative, did not fit the evidence. The debate underscored a truth that SETI researchers live by. The burden of proof is immense. To claim a message from another civilization requires eliminating every plausible natural explanation and demonstrating hallmarks of intelligence. The WOW signal easily satisfied the first criterion, defying conventional explanation. But it faltered on the second. It was strange, yes, but was it truly a message, or merely a natural mystery we lacked the tools to decipher? And so, 40 years later, the WOW signal endures as astronomy's most beguiling riddle. A single shout from the cosmos, heard once and never again, captured by a modest telescope in an Ohio field. It left us with no recording, no repeat, only a line of characters on fading paper, and the memory of one astronomer's astonished pen stroke. Whether it was a beacon from the stars or a trick of nature, its echo continues to guide the search, reminding us that the universe is vast, unpredictable, and still full of secrets waiting to be heard. Recent reanalysis has breathed new life into the mystery of the WOW signal. In the years 2024 and 2025, researchers returned to the fragile records of Big Ear, applying modern data processing tools unimaginable in the 1970s. From the faded archives, they extracted details once lost to noise, narrowing the possible region of origin, confirming the astonishing intensity of the transmission, and eliminating many classes of terrestrial interference that had long haunted the debate. Most intriguingly, subtle patterns emerged in the surrounding data hinting at a natural maser, a phenomenon in which clouds of hydrogen amplify radio waves under the influence of powerful cosmic events. The maser hypothesis has gathered momentum within the scientific community. Masers are the radio wave cousins of lasers, born when molecules in space become excited and begin to emit coherent radiation. Though rare, hydrogen masers have been documented in stellar nurseries and around aging stars. Researchers now propose that a transient hydrogen maser, perhaps sparked by a magnetar flare or the shock wave of a supernova, could have produced a burst that mimicked the very characteristics long associated with an intelligent beacon. Yet even this explanation does not resolve the wonder. If the WOW signal was indeed a natural hydrogen maser, it was unlike any previously observed, strikingly precise in frequency, elegantly shaped in time, and centered exactly on the cosmic channel that SETI researchers had championed as the most logical dial tone for interstellar communication. Coincidence begins to strain under the weight of such perfection. Whatever its origin, the WOW signal changed the landscape. It proved that Big Ear could catch interstellar whispers, validated the principles of SETI searches, and set a benchmark for credibility in anomalous detections. That benchmark now looms large as astronomers turn their instruments toward 3I Atlas, searching for echoes of that singular night nearly half a century ago. In the immense library of the electromagnetic spectrum, where every frequency carries its own chapter of the cosmic story, one particular wavelength has become more than a curiosity. It is a beacon, not merely to human scientists, but potentially to any mind across the universe that has ever lifted its gaze and wondered if it was alone. At precisely 1420.40575 MHz, hydrogen, the most basic and abundant element in existence, performs a trick of quantum subtlety. The lone electron orbiting its nucleus flips its magnetic orientation relative to the proton, releasing a single quantized note in the form of radio energy. This spin-flip transition is astonishingly rare on the scale of an individual atom, occurring on average once every 11 million years. Yet the cosmos is vast, and in the giant hydrogen clouds that span light years and contain uncountable trillions of atoms, the improbable becomes inevitable. The result is a constant, faint emission at 21 centimeters wavelength, a hum written into the background fabric of the universe itself. It is the music of matter, played by the element that makes stars, planets, and life possible. The true wonder of this frequency is not only its ubiquity, but its inevitability. Any civilization that stumbles upon radio astronomy will encounter the hydrogen line. They will measure its properties, record its exact value, and recognize its profound significance. It is not shaped by culture or biology, not bound to the quirks of any one world. It is a universal constant, a cosmic landmark, an address written into the laws of physics. This realization electrified the early pioneers of the search for extraterrestrial intelligence. In 1959, Giuseppe Cocconi and Philip Morrison published a paper that effectively launched modern SETI. They argued that the hydrogen line was nature's own interstellar calling frequency. Their reasoning was simple and elegant. If you wanted to craft a message that would be recognized anywhere, you would send it at the frequency that every species with a radio would inevitably discover. Later, researchers expanded this vision into what became known as the waterhole. This is a relatively quiet stretch of the spectrum, framed by the hydrogen emission at 1420 MHz and the hydroxyl molecule's signature around 1660 to 1670 MHz. In between lies a zone of relative calm, where cosmic noise recedes and signals stand out sharply. Bernard Oliver of Hewlett-Packard gave the idea a poetic flourish, calling it the closest thing to a universal quiet channel we are ever likely to find. The symbolism was irresistible. Hydrogen and hydroxyl, H and OH, are the raw ingredients of water, the liquid essential to life as we understand it. Just as living beings gather around watering holes to drink and communicate, perhaps advanced civilizations would congregate around this cosmic waterhole to exchange knowledge across the stars. Yet the hydrogen line's importance goes beyond poetry. Its physical traits make it ideal for long-distance communication. Radio waves at 21 centimeters slip easily through clouds of interstellar dust and gas that absorb or scatter other wavelengths. The line is inherently narrow-band, meaning that transmissions can be made efficiently with low energy demands and still stand out against the cosmic background. In recognition of its value, nations across the world have even set aside protections for this frequency, establishing quiet zones to shield it from human interference. When the WOW signal burst into the Big Ear telescope's receiver in 1977, its frequency 1420.455 MHz fell within 50 kHz of the hydrogen line. To researchers steeped in decades of SETI theory, the match was breathtaking. Here was the archetype they had envisioned, a narrow band, powerful, precisely placed signal, arriving from the sky like an intentional summons. It seemed to vindicate their intuition, a validation written in the numbers themselves. But the hydrogen line carries a paradox. Its natural prevalence also makes it a stage upon which nature performs its own elaborate dramas. Hydrogen masers, the radio wave cousins of lasers, arise when molecular clouds are energized by nearby astrophysical events. These cosmic radio lasers can emit narrow, intense signals at exactly the frequency that SETI researchers hope to find intelligent voices. Masers are found in star-forming regions, where newborn suns ignite their cradles of gas. They appear in the remnants of supernovae, where shock waves ripple through the interstellar medium. Even more dramatic phenomena, magnetar outbursts, gamma-ray flares, or the shredding of stars by supermassive black holes, might forge the fleeting conditions for maser bursts. This overlap creates what scientists call the natural mimicry problem. The very frequency we expect as the signature of intelligence is also the one where nature most convincingly fakes it. It is the cosmic equivalent of the boy who cried wolf, where genuine messages risk being drowned out or doubted because the universe itself knows how to imitate their form. In this way, the hydrogen line embodies both the promise and the peril of SETI. It is the most logical frequency to listen for, and the most treacherous to interpret. Modern searches for extraterrestrial intelligence have grown far more sophisticated than those of earlier decades, precisely to grapple with the challenge of separating genuine messages from nature's own convincing imitations. Researchers now hunt for qualities that the cosmos rarely produces by accident: intricate modulation patterns that suggest deliberate design, frequency drifts carefully compensating for the motion between transmitter and receiver, or structured bursts of information that bear the unmistakable imprint of encoding. Just as important is repeatability. A signal that emerges more than once from the same celestial coordinates speaks with a persistence that natural flukes seldom manage, strengthening the case for an intentional source rather than a solitary anomaly. The idea of the waterhole, once tightly bounded by hydrogen and hydroxyl frequencies, has also matured. Some scientists propose widening the search to include other molecular transitions of biological relevance. The ammonia line near 23 GHz, signatures from complex organic molecules, and even relatively quiet windows in the cosmic microwave background have been suggested as alternative rendezvous points for interstellar communication. The concept has become more fluid, yet despite these expansions, the hydrogen line still holds a special, almost mythic status. Large projects continue to devote immense resources to it. The Breakthrough Listen initiative, the most ambitious SETI effort in history, routinely scans hydrogen line frequencies with exquisite precision. China's colossal 500-meter aperture spherical telescope dedicates a significant fraction of its time to this same spectral band. Even optical SETI experiments sometimes anchor their search strategies on laser emissions that correspond to hydrogen transitions in the visible spectrum. The reason is simple. If humanity ever decides to declare its presence to the cosmos, the hydrogen line remains the most compelling frequency to choose. It is instantly recognizable, deeply significant, and almost impossible to mistake for anything other than an intentional signal. Recent technological leaps have made the search more powerful than ever. State-of-the-art receivers can distinguish signals separated by mere hertz across bands that stretch for millions of hertz. Polarization data can be teased apart, revealing details of distant magnetic environments. Most transformative of all, vast computing systems can now process torrents of data in real time, enabling immediate follow-up observations of suspicious signals. No longer must astronomers wait weeks for analysis to catch up. Now they can pivot telescopes within moments to verify a fleeting anomaly. All of this progress comes into sharp focus as 3I Atlas glides through our solar system. If, by some extraordinary chain of connection, this interstellar traveler and the WOW signal share a common origin, then the best chance to catch a repeat message would be during the comet's intimate encounters with major planetary bodies. The hydrogen line once again becomes our guiding frequency, precisely defined, universally significant, and fiercely protected from interference. As the visitor approaches Mars, swings past the Sun, and brushes near Earth, observatories across the globe will be tuned to that same band, where a mysterious signal once startled an astronomer with a red pen. Whether silence or revelation greets them, the act of listening itself matters most. It embodies our ongoing vow to ask whether we are alone, and our determination to listen for voices speaking in the most fundamental language the universe has to offer. In science, reproducibility is everything. A discovery that refuses to repeat itself lingers in a limbo between marvel and mistake, too important to dismiss, yet too fragile to accept as truth. For 48 years, the WOW signal has occupied exactly this purgatory. It is a mystery, immortalized by Jerry Eamon's red pen, a single burst of data that hinted at a voice from the stars, but never returned to confirm its existence. The pursuit of replication began almost immediately. Within weeks of the signal's arrival from Sagittarius in August of 1977, radio telescopes around the world turned their ears to the sky, straining to catch the voice again. The Big Ear team themselves mounted repeated campaigns through the late 1970s and into the early 1980s, sweeping the same region night after night. What they heard was only silence. Yet hope endured. The Very Large Array in New Mexico, with its unmatched resolution and sensitivity, joined the hunt. Arecibo's vast dish, capable of detecting signals far fainter than Big Ear had ever been designed to capture, combed through the suspected coordinates. In Australia, Parkes Observatory offered coverage from the southern hemisphere, ensuring that no angle was left unchecked. International collaborations sprang into existence, pooling instruments, expertise, and precious observing time in a global effort to trap lightning in a bottle for a second time. As technology advanced, so too did the search. Bulky analog receivers gave way to modern digital systems with dramatically improved sensitivity. Computers could now record immense swaths of the spectrum in real time, preserving every fluctuation for later study. Sophisticated algorithms replaced the human eye, scanning for narrow band emissions that once might have slipped unnoticed through printed charts. The tools became sharper, the listening more patient. And yet, through all these years of vigilance, the cosmos offered no encore. This absence was damning and tantalizing in equal measure. Natural astronomical sources tend to reveal themselves through repetition. Pulsars tick like metronomes. Variable stars brighten and fade with reliable rhythm. Even phenomena once thought to be singular, such as gamma-ray bursts or fast radio bursts, have shown themselves to belong to categories of recurring events. By contrast, the WOW signal's defiant solitude unsettled expectations. It was a solitary flash, a one-time note in a symphony that never played again. By the dawn of the 21st century, skepticism began to outweigh wonder. Some astronomers consigned the WOW signal to the category of unexplained terrestrial interference. Perhaps Big Ear's electronics, already aging by the late 1970s, had suffered a momentary fault. Maybe stray reflections from a passing aircraft had created the illusion of a cosmic transmission. Others speculated about microwave ovens or other mundane sources of radio leakage, coincidentally aligned with the telescope's beam. The WOW signal seemed destined to fade into the footnotes of scientific history, a mystery explained away by hardware quirks or human error. But the reanalyses of 2024 and 2025 reopened the case in dramatic fashion. A team led by scientists at the National Radio Astronomy Observatory revisited the original data archives with the tools of a new century. Advanced processing techniques teased out subtleties invisible to earlier generations. What emerged was not the picture of a mundane glitch, but of a signal more extraordinary than even Eamon might have imagined. First, they narrowed its origin. By reconstructing the Big Ear's beam shape and carefully modeling the signal's intensity curve, the researchers confined its likely source to a patch of sky only 8 arc minutes across, about 1/4 the apparent size of the full moon. Such precision effectively ruled out terrestrial interference and pointed instead to a genuine astronomical point source lying far beyond Earth. Second, they recalibrated its strength. Where earlier estimates had been conservative, the new analysis suggested that the signal's peak flux density may have exceeded 250 Janskis. In practical terms, this made it one of the most powerful radio emissions ever recorded outside the solar system. For context, the Crab pulsar, one of the most luminous radio objects in the Milky Way, registers as nearly 50 times weaker at comparable frequencies. Most tantalizing of all, the reanalysis uncovered faint, structured patterns in the surrounding data details overlooked for decades, now revealed through the sharpened eyes of modern computation. These subtle traces did not resolve the mystery, but they shifted the narrative once again, suggesting that the WOW signal may not have been a meaningless spike of noise after all. Instead, it might have been the leading edge of a phenomenon we still do not fully understand, a whisper from the universe that we have only just begun to translate. Weak enhancements were discovered at neighboring frequencies and times, subtle ripples in the data that suggested the main WOW signal might not have been a lone spike at all, but part of a richer and more complex emission structure. To modern eyes, sharpened by decades of astrophysical experience and the power of advanced computation, these patterns looked tantalizingly consistent with what one might expect from a hydrogen maser caught in rapid, chaotic evolution. Out of this reanalysis has emerged the leading natural explanation for the most famous mystery in SETI, the maser hypothesis. Masers, the cosmic cousins of lasers, are born when interstellar molecules, energized by nearby astrophysical events, fall into conditions that create coherent amplification of radio waves. When this happens, the emission can be narrow-band, extraordinarily bright, and eerily similar to what a deliberately engineered signal might look like. Hydrogen masers, while rare, have been detected in dense star-forming regions and around dying stars shedding their outer layers. The recipe is precise. A cloud of hydrogen gas must be illuminated by a surge of energy, a magnetar flare, the shockwave of a supernova, or even the searing flash of a gamma ray burst in some distant galaxy. That energy drives population inversions within the hydrogen atoms, a reshuffling of their electrons that primes them to act like amplifiers. As the radiation pulse passes through, the cloud lights up in stages, producing a transient maser emission at the 21-centimeter hydrogen line. Such a beacon might blaze for mere minutes or hours before dissipating forever into silence. This model, for many, solves several of the WOW signal's puzzles. It explains the uncanny match to the hydrogen line, the razor-thin bandwidth, and the staggering intensity that made the signal 30 times brighter than background noise. Maser amplification could indeed provide the raw power required. Most critically, it accounts for the silence that followed. If the maser was triggered by a singular astrophysical event, the conditions would never be recreated, and the signal would remain a one-time apparition. Yet even this naturalistic explanation leaves behind a residue of wonder. If the WOW signal was a hydrogen maser, it would represent a category of astrophysical event never directly observed before or since. The timing is also difficult to ignore, that it flared precisely at the frequency where humans were mounting their most ambitious SETI efforts, at the moment when attention was fixed on the hydrogen line as a universal beacon, stretches coincidence to its breaking point. And then there is location. The signal came from the same region of Sagittarius that has now, decades later, sent us 3I Atlas, our most enigmatic interstellar visitor. For some, this alignment of time, place, and theory begins to feel less like chance and more like a cosmic riddle. Critics of the maser hypothesis point out its difficulties. To generate a signal of such intensity would require energy inputs on the scale of stellar cataclysms. Events of that magnitude should echo across the spectrum, producing X-ray flashes, gamma-ray afterglows, or optical signatures. Yet, in the days and weeks surrounding August of 1977, no such counterparts were recorded from Sagittarius. A maser, strong enough to mimic the WOW signal, may stretch plausibility, almost as far as invoking intelligence. This debate underscores the central paradox of SETI. The universe is astonishingly inventive. Again and again, phenomena once suspected of being technological have turned out to be natural. Pulsars ticked so precisely that their discoverers half-seriously labeled them little green men before neutron stars entered the textbooks. Fast radio bursts, with their dazzling intensity and bizarre dispersion patterns, ignited speculation about interstellar technology until accumulating data traced them back to magnetars and other exotic but natural origins. The WOW signal resides at this same uneasy frontier, where known and unknown blur, where natural and artificial imitate one another perfectly. Its refusal to repeat does not disprove the alien hypothesis. A civilization might have transmitted a single message, a flare into the void, before vanishing in catastrophe or simply turning their instruments elsewhere. But its perfect alignment with the hydrogen line does not prove intelligence either, for nature has shown a startling ability to mimic the very signals we most expect. What remains is a productive uncertainty, the kind that propels science forward. The WOW signal forced astronomers to refine their strategies, to build more sensitive receivers, to invent more powerful algorithms. It set benchmarks for credibility in SETI research, standards that still shape how we evaluate every anomaly today. And those standards matter now more than ever as we confront the mystery of 3I Atlas. Unlike radio waves, which vanish into the ether without leaving a trace, this interstellar traveler offers the gift of repeatable measurement. We can analyze its chemistry, chart its trajectory, and listen for whispers as it brushes past our worlds. It poses the question that has haunted SETI from the beginning. Are we confronting two separate enigmas, or are the WOW signal and 3I Atlas fragments of something larger, pieces of a message we have only just begun to read? When ancient stargazers lifted their eyes to the constellation Sagittarius, they imagined the outline of a centaur archer, his bow drawn tight, aiming his arrow at the luminous heart of the Milky Way. What they could not have known was that their mythic image concealed one of the most extraordinary neighborhoods in the galaxy, a realm where gravity, radiation, and raw energy collide on scales that defy ordinary comprehension. Today, when we look towards Sagittarius, we are not simply tracing patterns of stars projected onto the dome of the night sky. We are peering directly into the galactic center itself, the true gravitational anchor of the Milky Way. Some 26,000 light-years away, hidden behind curtains of interstellar dust, lies Sagittarius A star, a supermassive black hole weighing the equivalent of 4.3 million suns. This immense engine of gravity holds the galaxy together, its invisible pull choreographing the orbital dance of hundreds of billions of stars. Occasionally, its hunger becomes visible when unlucky clouds of gas or wandering stars drift too close and are torn apart, their remains spiraling inward and flaring brightly before vanishing across the event horizon. Around this cosmic monster, matter churns, collides, and collapses with an intensity that rewrites the rules of space itself. The environment surrounding Sagittarius A star could scarcely be more alien to us. In our quiet spiral arm suburbs, stars are separated by light years of empty space. Near the galactic center, stellar density climbs so high that planetary systems would struggle to survive the constant gravitational tugs of neighbors. Radiation levels surge to intensities that could strip atmospheres bare or sterilize worlds outright. Magnetic fields twist, reconnect, and snap with energies that make Earth's storms seem like whispers. Here, chaos reigns, but in that chaos lies a treasure trove for astronomers. Radio astronomers in particular find Sagittarius both irresistible and maddening. The region radiates more strongly at radio frequencies than any other direction in the sky. It was from Sagittarius that Carl Jansky, in 1932, first detected radio waves from beyond Earth, unknowingly founding an entirely new branch of astronomy. Every class of radio source known today, pulsars spinning with metronomic precision, the ghostly shells of supernova remnants, sprawling stellar nurseries birthing suns, and planetary nebulae, glowing with the last sighs of dying stars, exists in abundance along this line of sight. Add to these the still mysterious phenomena that defy neat classification, and Sagittarius becomes both a laboratory and a labyrinth. For researchers in the search for extraterrestrial intelligence, this complexity is a double-edged sword. On one hand, the density of stars offers opportunity. The galactic center packs thousands of stellar systems into volumes smaller than the gulf that separates us from even our nearest stellar neighbors. If a civilization wished to establish a communication hub, there could scarcely be a more strategic position. A single broadcast could sweep across multitudes of worlds, maximizing reach in a single gesture. On the other hand, the region's overwhelming radio noise creates a nearly insurmountable obstacle. Detecting a faint artificial signal amid this natural roar is like trying to pick out a whispered voice in the middle of a crowded city square at rush hour. Astronomers call this the cocktail party problem, how to focus on one voice when all others speak at once. The WOW signal appeared against precisely this backdrop, which makes its clarity even more astonishing. Despite the maelstrom of emissions from the galactic center, the signal cut through as narrow band, powerful, and centered on a frequency of profound significance. Its ability to stand out amid such noise suggested either an artificial transmitter of remarkable precision or a natural phenomenon of rare coherence, such as a hydrogen maser flaring at just the right moment. It is important to remember, however, that Sagittarius is vast. The constellation spans about 30 degrees across the sky, equivalent to 60 full moons laid side by side. To say that both the WOW signal and 3I Atlas originated from Sagittarius is to gesture toward an enormous region teeming with activity. The coincidence, striking as it may seem, must be weighed against the statistical reality that this direction hosts some of the most energetic and enigmatic sources in the galaxy. And yet, the allure remains. Whether mythic archer or cosmic furnace, Sagittarius continues to focus our attention on the mysteries written into the heart of the Milky Way. Even when we account for the immense angular scale of Sagittarius, the directional correlation between our two mysteries remains difficult to dismiss. The WOW signal's location, recently constrained to within 8 arcminutes, sits in the same general swath of sky from which 3I Atlas now appears to approach. Statistically, this could be nothing more than coincidence. Yet, it is precisely the kind of coincidence that keeps astronomers awake at night, because coincidences in the sky often serve as invitations to look more closely. The physics of interstellar space further complicates the story. Any object arriving in our solar system from the direction of Sagittarius has traversed a gauntlet of forces and environments. It has passed through gravitational fields, distorted by the pull of massive star clusters. It has endured radiation fields intense enough to transform surface chemistry in ways no local comet has experienced. It has threaded its way through tangled magnetic regions where charged particles bend and twist in unpredictable paths. If 3I Atlas truly originated along the Sagittarius sightline, then it has survived this cosmic obstacle course, carrying scars and signatures written into its very structure. Its chemistry bears this out. Observations suggest an unusually high ratio of carbon dioxide to water vapor, nearly 8:1, the reverse of what we typically find in solar system comets. Even stranger is the detection of nickel without corresponding iron, a pairing almost unheard of in our own backyard. Such anomalies may hint at birth conditions around a different kind of star, or perhaps reflect exposure to environments more extreme than any within our solar neighborhood. Either way, the object's characteristics speak of a history that diverges sharply from the comets we know. Sagittarius matters for reasons beyond geometry or chemistry. It matters because of demographics and strategy. If advanced civilizations do exist in the Milky Way, they are most likely to arise around long-lived, stable stars enriched with the heavy elements required for complex chemistry and planet building. The galactic bulge, and particularly the region near the galactic center, contains some of the oldest, most metal-rich stars in our galaxy. Though bathed in intense radiation, it offers fertile ground for worlds with the ingredients of life. From the perspective of interstellar communication, the galactic center provides something even more compelling: reach. A transmitter placed within the bulge could project across vast portions of the disk, illuminating thousands of systems at once. It is the cosmic equivalent of broadcasting from the highest mountain peak, where a single beacon can cover the widest territory. This strategic advantage is one reason early SETI researchers concentrated their attention both on the hydrogen line frequency and on the galactic center. They reasoned that if someone wished to announce their presence, this was where they would plant their flag, and this was the channel they would use. Meanwhile, modern surveys are revealing how little we have yet seen of interstellar traffic. The upcoming Legacy Survey of Space and Time, conducted by the Vera Rubin Observatory, is expected to multiply our census of interstellar objects by hundreds, perhaps thousands. What we now treat as rare events, Oumuamua in 2017, Borisov in 2019, 3I Atlas today, will likely become statistical populations. Most of these newcomers will arrive from random directions, their paths shaped by the chaotic dispersal of ejected debris across billions of years. But if 3I Atlas remains unusual, if its chemistry, its behavior, or any associated phenomena set it apart, then its arrival from Sagittarius gains extra weight. Chance becomes less convincing when anomalies begin to cluster in both time and space. Sagittarius has already given us two enigmas that resist easy explanation: a radio signal that sang once and then disappeared, and a comet-like wanderer from beyond the stars that refuses to behave like any comet we know. Whether these threads are woven together or merely lie side by side, they push us toward the same unsettling horizon. They remind us that our cosmic neighborhood may be far livelier, more connected, and more filled with intention than we have dared to assume. As 3I Atlas continues inward, first drawing near Mars in early October and then swinging around the Sun, we will have opportunities to listen. If radio telescopes detect even a faint murmur near 1420 MHz, the same frequency where the WOW signal once flared, the coincidence will no longer be possible to shrug away. And if silence prevails, that too will teach us something. It will remind us that Sagittarius, with all its violence and wonder, continues to surprise, to unsettle, and to humble. It will remind us that the sky is a library full of mysteries waiting for discovery, each one a challenge to our certainty and an invitation to our imagination. On the 1st of July, in the year 2025, while most of humanity lay in slumber, the desert skies of Chile bore silent witness to history. The Atlas Survey, the asteroid terrestrial impact last alert system, had long kept vigil in the Atacama, its automated cameras sweeping the heavens with tireless precision. For years it had catalogued the patient ballet of asteroids bound securely to the sun's embrace, guardians of data, but rarely of drama. That night, however, the routine fractured. Against the fixed tapestry of background stars, an object moved with a swiftness that triggered every alert in the system's algorithms. This was no familiar member of our celestial family. Its trajectory screamed of exile, a hyperbolic arc bending briefly around the sun, not out of loyalty, but by necessity, a path that declared, "I do not belong here." Oh, John Tonry, principal investigator of the Atlas program, and his team swiftly grasped the enormity of what they had found. Orbital calculations confirmed the impossible, an eccentricity greater than 1, the unambiguous mark of an interstellar traveler. This was not an asteroid drifting too far from its belt, nor a long-period comet returning from the Oort cloud's frozen reservoir. Designated 3I Atlas, the object was foreign, born in another stellar nursery, and flung across the gulf of space to arrive, briefly, in our skies. Within hours, the discovery electrified observatories across the globe. Telescopes turned their mirrors toward the stranger, racing to capture every detail before its fleeting passage carried it once more into the silence between stars. Unlike its predecessor Borisov, which was discovered only after passing perihelion and was already racing back into interstellar night, 3I Atlas was still inbound when it first revealed itself. That difference granted astronomers a rare gift: months of close study, a chance to watch an interstellar traveler awaken under the light of our Sunday. From the outset, it showed itself to be unlike anything in our familiar cosmic neighborhood. As the object approached the inner solar system, solar radiation began to rouse frozen volatiles trapped within its compact nucleus. A hazy coma of gas and dust appeared, the archetypal cloak of a comet, followed soon by the growth of a tail arcing away from the Sunday. Yet this was no ordinary comet. Early spectroscopic studies quickly revealed chemistry that did not align with expectations built from decades of observing native solar system bodies. The James Webb Space Telescope, peering in infrared, detected startlingly high concentrations of carbon dioxide compared with water vapor, with a ratio approaching 8:1. Most comets in our system display the opposite balance, dominated by water. This inversion immediately suggested that 3I Atlas was born in an environment profoundly different from our own. The Hubble Space Telescope contributed crucial size estimates. High-resolution imaging placed the nucleus's upper limit at about 5.6 kilometers across, though some analyses hinted it might be far smaller, perhaps as compact as 320 meters. If so, its prodigious outgassing represented a level of activity far beyond expectation, what astronomers delicately termed overperformance. A body so small, yet so vigorous, challenged conventional models of cometary physics. Ground-based observatories soon added further layers to the puzzle. The Gemini South Telescope in Chile captured vivid images of the coma's expansion and the tail's changing geometry, charting their development as the visitor drew closer to the Sunday. Meanwhile, the Very Large Telescope conducted detailed spectroscopic sweeps that revealed a peculiarity in elemental composition. Emission lines of nickel shone clearly in the data, but iron, a companion element almost always present in tandem, was absent or undetectable. Since nickel and iron typically share formation pathways and chemical affinities, their separation in this case provoked spirited debate among planetary scientists. Its orbital characteristics only deepened the intrigue. 3I Atlas arrived on a retrograde trajectory, moving around the Sun opposite the direction of the planets and most resident objects. Its inclination of about 5 degrees placed it nearly in the same plane as the solar system's architecture, yet it traveled against the current, like a lone vehicle driving the wrong way down a crowded highway. This unusual geometry further emphasized its foreignness, marking it as a true outsider. Through late summer, the spectacle continued to build. By August, astronomers reported vigorous water emission joining the already rich cocktail of gases, inflating a temporary atmosphere of dust and vapor around the nucleus. Telescopic imaging campaigns documented the classic curvature of the tail as solar wind and radiation pressure sculpted the outflow into elegant arcs. The same celestial artistry that has fascinated humans is for millennia. And yet, for all its exotic traits, 3I Atlas remained frustratingly faint. Its maximum predicted brightness of magnitude 11 to 13 placed it far below the threshold of naked eye visibility. Unlike the dazzling apparitions of Hale-Bopp or Hyakutake, this comet would never dominate the night sky. It was destined instead to remain an astronomer's object, visible only to dedicated observers and the world's most powerful instruments, a subtle signature of something alien threading briefly through our solar system before vanishing once more into the stars. When word of 3I Atlas's discovery spread, safety concerns understandably dominated early public discussion. NASA and other international space agencies moved swiftly to calculate its orbit with precision. Their findings brought relief. At no point during its journey would the visitor pose a danger to Earth. Its closest approach would occur on the 19th of December, 2025, passing at a comfortable 270 million kilometers, about twice the distance between Earth and the Sunday. With that reassurance came excitement. This was only the third confirmed interstellar object ever seen within our solar system. The first, Oumuamua in 2017, had defied neat classification with its elongated shape and unexplained acceleration. The second, Borisov, in 2019, looked more familiar, a comet complete with coma and tail, yet its chemistry bore the unmistakable stamp of an alien birthplace. Now, 3I Atlas promised to be different still. Unlike its predecessors, it was inbound at discovery, affording months of study. Every instrument in modern astronomy could be turned toward it, from ground-based telescopes to spaceborne observatories, all collecting data from this authentic fragment of another star system. What made the discovery even more intriguing was its direction of approach. The interstellar visitor traced its path back towards Sagittarius, the same crowded region of sky where, nearly half a century earlier, the WOW signal had been detected. The overlap might be nothing more than chance. The constellation spans vast angles of sky, but coincidences of this kind linger in the minds of astronomers. As professional teams and amateur skywatchers alike followed the object, a question quietly accompanied each observation. Was 3I Atlas merely a random piece of planetary debris, or could its arrival somehow echo that mysterious signal from 1977? As data accumulated through the summer of 2025, the comet's strangeness deepened. Spectra from the James Webb Space Telescope revealed a chemistry unlike anything native to our solar system. Instead of water dominating its volatile inventory, carbon dioxide appeared in overwhelming abundance. The ratio of carbon dioxide to water stood at roughly 8:1, the reverse of what we normally see. This inversion implied birth conditions far removed from those that shaped our local comets, perhaps around a hotter star or in an environment rich in different heavy elements. It suggested that 3I Atlas carried within it a record of chemical processes foreign to our own solar nursery. Meanwhile, the Hubble Space Telescope offered size constraints that only sharpened the paradox. Its imaging placed the nucleus at no more than 5.6 kilometers across, with some models reducing that estimate to a fraction of a kilometer, a body no larger than a city. And yet, despite its modest bulk, the comet produced activity rivaling objects many times larger. Its coma expanded into a tenuous envelope, hundreds of thousands of kilometers wide. Its tail stretched for millions of kilometers, a vast plume sculpted by sunlight into the classic arc humanity has watched for millennia. This vigorous display earned the label overperformance among comet scientists. Ordinarily, small nuclei cannot sustain such outbursts. They possess too little surface area to absorb solar heat, and too little frozen material to release. Yet 3I Atlas seemed to defy this rule, sublimating volatile compounds with an efficiency out of proportion to its size. For cometary physicists, this raised troubling questions. Was its surface unusually porous, exposing more active area than expected? Did its chemistry unlock new mechanisms of gas release? Or was it shaped by entirely different processes beyond those familiar to our solar system? Thus, by late 2025, 3I Atlas stood revealed as an interstellar paradox, safe yet significant, modest in size yet extravagant in performance, chemically alien yet cosmically familiar. Its coincidence of direction with the WOW signal remained unresolved, but its mysteries were undeniable. In its faint light and ghostly trails, astronomers glimpsed not just a wandering comet, but a fragment of another world, carrying with it questions that no single observation could yet answer. The object seemed to be following a different set of rules, as though its compact nucleus was either unusually rich in reactive materials or structured in a way that maximized the release of volatile compounds. This suspicion gained strength when spectroscopic surveys revealed yet another anomaly. The Very Large Telescope in Chile detected strong emission lines from nickel atoms glowing within the comet's coma. Normally, this would not have raised eyebrows. Nickel is a familiar presence in cometary spectra, but what was missing proved more perplexing. Iron, nickel's constant companion in cosmic chemistry, was absent. In nearly every environment studied asteroids, meteorites, comets, nickel and iron appear together, forged side by side in stellar furnaces and bound within similar mineral phases. When cometary material vaporizes under solar heating, both elements usually announce themselves in predictable ratios. Yet 3I Atlas seemed to be breaking that pattern, producing abundant nickel while keeping iron hidden below detection thresholds. Scientists rushed to propose explanations. Perhaps the iron was locked within compounds that required higher temperatures to volatilize, meaning its signal would emerge only when the comet drew closer to the sunday. Others argued that the object's birth environment might have been skewed, favoring nickel-rich minerals over iron. In that case, its unusual chemistry would not be a trick of observation, but a true fingerprint of a foreign stellar nursery. Its orbit, too, contributed to the sense of strangeness. 3I Atlas arrived on a retrograde trajectory, moving opposite the direction of planets and most other solar system objects. Its inclination was modest, only about 5 degrees, meaning it traveled nearly in the same plane as the planets but against their traffic, like a lone car heading the wrong way down a vast interplanetary highway. Retrograde motion is not impossible for natural wanderers, but the odds are low. Most ejected material from planetary systems arrives with orbits scattered in all directions. To find one moving retrograde yet aligned with our ecliptic seemed another coincidence in a discovery already rich with them. As the summer of 2025 unfolded, the comet only grew more confounding. Its activity levels surged well beyond expectations, even while it was still more than 3 astronomical units from the sun distances where most comets from the outer solar system remain inert. The fact that 3I Atlas was already producing a luminous coma and tail so far out suggested either an unusually volatile composition or an extraordinary sensitivity to solar radiation. These accumulating puzzles inevitably attracted researchers willing to consider more radical interpretations. Avi Loeb of Harvard University, who had earlier suggested that Oumuamua might be technological in origin, began to examine the data from 3I Atlas with similar questions in mind. He pointed to the comet's overperformance, its carbon dioxide dominance, and its nickel-heavy chemistry as possible technosignatures, perhaps evidence of manufactured materials or byproducts of industrial processes. The astronomical mainstream responded with skepticism, reminding the community that extraordinary claims demand extraordinary proof. Jason Wright of Penn State and others argued that while unusual, the anomalies remained within the range of natural possibilities. They noted that 3I Atlas still behaved like a comet in crucial ways. It developed a coma and tail, responded to solar heating, and followed a gravitational path without any sign of controlled motion. The chemistry, however odd, might simply reflect formation under conditions unlike those of our solar system, and yet, even the skeptics conceded that the comet was unprecedented. Its chemistry, compact size, vigorous activity, and coincidental approach from the same region of sky as the WOW signal created a pattern that could not easily be ignored. As autumn approached, and 3I Atlas neared its encounters with Mars and the Sun, the central question remained unresolved. Was this merely an unusually exotic natural object, or a technological artifact carrying a message from beyond? The answer would depend on whether its anomalies reflected alien engineering or simply the limits of our knowledge about how worlds form in stellar nurseries far different from our own. In the cosmic game of connecting the dots, astronomy often resembles a puzzle assembled from faint traces and scattered clues. Sometimes patterns emerge that are too striking to ignore, even when statistical caution urges restraint. The apparent directional alignment between the WOW signal and 3I Atlas is precisely this kind of pattern, compelling enough to demand attention, elusive enough to resist definitive interpretation. Trajectory analyses by NASA confirmed what early observations had suggested. 3I Atlas was indeed inbound from the general direction of Sagittarius. More specifically, its radiant, the point on the celestial sphere from which its motion appears to originate, fell within the same broad swath of sky where the WOW signal had been recorded nearly half a century earlier. The overlap was not exact. Uncertainties in both measurements left degrees of separation, but the match was close enough to qualify as what astronomers call a positional coincidence, the kind of alignment that, while not proof of connection, cannot be casually dismissed. Understanding the significance of this overlap requires attention to scale. Sagittarius, as defined by constellation boundaries, stretches across roughly 30 degrees of sky, an expanse equivalent to 600 full moons tiled together. Within this canvas, the WOW signal's refined coordinates now occupy a patch about 8 arcminutes across, while the radiant of 3I Atlas spans a similarly sized ellipse, displaced by a few degrees. Statistically, this hardly constitutes evidence of linkage. Sagittarius represents about 1/15 of the entire celestial sphere, meaning random chance alone would predict that around 7% of unusual phenomena should trace back to its direction. With a sample size of 2, statistical inference collapses into meaninglessness. And yet, Sagittarius is not an ordinary patch of sky. It points directly toward the galactic center, the beating heart of the Milky Way, where star densities soar to levels unimaginable in our quiet spiral arm. Here, stellar populations pack so tightly that planetary systems may be constantly disrupted by gravitational encounters. Radiation levels spike, magnetic fields twist chaotically, and matter swirls in violent interaction with the supermassive black hole Sagittarius A star. From one perspective, this makes the galactic center a hostile wasteland. From another, it marks the galaxy's most fertile ground for cosmic drama. For SETI researchers, Sagittarius is both temptation and torment. The region's crowded stellar populations suggest enormous potential for habitable worlds and advanced civilizations. Thousands of stars lie within volumes far smaller than the distances separating us from even our nearest neighbors. A civilization seeking to maximize its reach would find in the galactic bulge an ideal broadcasting platform. From there, powerful beacons could sweep across vast swaths of the Milky Way, touching countless planetary systems with minimal energy expenditure. Conversely, the region's cacophony of natural radio emissions makes it a bewildering environment for signal detection, the cosmic equivalent of trying to overhear a whisper in the middle of a bustling city square. It was precisely this strategic logic that influenced the earliest SETI programs. Researchers reasoned that if intelligent species sought to establish a communication hub, the galactic center was the obvious location, and the hydrogen line frequency the obvious channel. That logic continues to shape modern searches. Sagittarius remains both the most promising and the most frustrating direction to listen, the place where one most expects to find evidence of intelligence, and the place where such evidence is most difficult to distinguish from nature's own extravagances. The correlation between the WOW signal and 3I Atlas becomes even more intriguing when viewed through the lens of galactic dynamics. Objects ejected from planetary systems near the galactic center would naturally spread outward over millions of years, drifting through interstellar space until some happen to wander into the solar system. If 3I Atlas truly originated along the Sagittarius line of sight, it may be a fossil fragment of world-building processes from the galaxy's most energetic nursery, an emissary carrying chemistry forged under conditions alien to our own. But what unsettles most is not just the directional coincidence, it is the timing. If 3I Atlas has indeed wandered for millions or even billions of years since its ejection, the odds that it would arrive precisely during the brief sliver of human history when radio astronomy exists, and so soon after we detected an unexplained signal from the same general direction, stretch the concept of chance to breaking. Temporal coincidence compounds spatial coincidence, creating a pattern that, though built from only 2 data points, forces us to wonder whether randomness alone can account for such alignment. The universe has endured for 13.8 billion years, a span so vast that human history scarcely registers against it. Our species has wielded radio technology for less than 150 of those years, a blink within cosmic time. Against that backdrop, the probability that 2 entirely unrelated phenomena, a mysterious radio transmission and a visiting interstellar comet, should both intersect with our tiny planet during this minuscule interval, seems vanishingly small. And yet, timing can be interpreted in 2 ways. If 3I Atlas were not a random wanderer, but rather an object deliberately directed toward the solar system, its arrival now would make sense. In that scenario, the comet might function as an autonomous probe or as part of a broader interstellar communication network, a deliberate response to our growing visibility as a technological species. The logic is seductive. As soon as humanity announces itself through radio, the galaxy answers back with both signal and messenger. But such speculation demands evidence, and at present, none exists that would elevate these ideas beyond conjecture. All current observations of 3I Atlas point toward natural origin. It behaves as a comet, shedding dust and gas under solar heating. Its spectral signatures resemble those of volatile rich nuclei, however exotic the exact chemistry may be. Its trajectory follows the strict dictates of gravity, without any hint of controlled maneuvering. Even its anomalies, the carbon dioxide dominance, the selective nickel emission, the vigorous outgassing remain within the outer limits of what might plausibly occur in unfamiliar planetary systems. Still, the coincidence nags. 2 of the most perplexing astronomical anomalies of the modern era, separated by nearly half a century, both trace back towards Sagittarius, the galaxy's gravitational hub where environments grow strange and extreme. Perhaps the link is nothing more than a trick of perspective, our pattern-hungry minds weaving threads where none exist. Perhaps it simply reflects the galactic center's natural propensity for producing rare and energetic phenomena. Or perhaps, just perhaps, it hints that our corner of the cosmos is more active and more interconnected than we have dared to imagine. Definitive answers will not come soon. To determine whether these alignments are meaningful or coincidental, we need far larger samples of both interstellar objects and unexplained radio bursts. The forthcoming Legacy Survey of Space and Time promises to expand our catalogue of interstellar wanderers by hundreds or even thousands, allowing us to see whether 3I Atlas is a singular oddity or part of a larger population. Meanwhile, advances in radio astronomy, greater sensitivity, better data pipelines, and real-time processing will increase the odds of detecting transients like the WOW signal. should similar bursts recur from the Sagittarius direction, particularly if timed with the comet's passage, coincidence will become a far less satisfying explanation. For now, we are left with questions rather than conclusions, patterns rather than proofs. The universe has offered us two enigmas from the same patch of sky, and it is up to us to decide whether we are glimpsing random alignment or the first hints of a story larger than our imagination has yet allowed. As 3I Atlas drifts deeper into the solar system, each new observation brings us either closer to clarity or further into mystery. The celestial choreography guiding 3I Atlas through our solar system has been mapped with the exquisite accuracy that only gravitational mechanics can provide. Unlike the enigmatic wow signal, which flared once and vanished forever, the comet follows a predictable itinerary that gives us multiple chances to observe it and, perhaps, to address questions that have lingered for nearly half a century. The first major encounter will arrive swiftly. In early October of 2025, 3I Atlas will pass within 30 million kilometers of Mars. This distance, while vast in everyday terms, places it well within range of spacecraft already orbiting the red planet. The European Space Agency has confirmed that its operational assets, including the ExoMars Trace Gas Orbiter and Mars Express, will attempt coordinated campaigns during the flyby. For the first time, humanity will have spacecraft poised to capture an interstellar visitor from several vantage points at once. These stereoscopic perspectives may yield insights into its shape, rotation, and surface features that Earth-based telescopes could never resolve. The geometry of the encounter may even allow subtle measurements of the object's gravitational tug on nearby spacecraft, potentially constraining its mass and probing the mystery of its interior structure. This Martian flyby, timed for around the 2nd and 3rd of October, coincides with a period of peak solar heating. The comet's volatile inventory will be most active, its coma and tail most vigorous. Spectroscopic surveys in this window will be crucial. Researchers hope to determine whether the peculiar nickel emission lines continue to shine, and whether long-absent iron finally reveals itself as the nucleus grows warmer. After its passage by Mars, 3I Atlas will curve inward toward perihelion, its closest approach to the Sun, on the 29th and 30th of October. At that moment, it will lie about 1.4 astronomical units from the star, within the orbit of Mars but still comfortably beyond Earth's track. Perihelion is always the crucible for comets, when solar energy sculpts them most violently. Outbursts, fragmentation, and rapid changes in brightness often occur during this phase. If the comet conceals any unusual qualities, whether exotic materials, strange internal architecture, or something more provocative, perihelion will be the time when they are most likely to emerge. Yet, this critical interval comes with frustrating limitations. From Earth's vantage point, the comet will appear too near the Sun's glare for safe observation. Ground-based instruments will be effectively blinded for weeks. Only space telescopes, equipped with the necessary shielding, such as Hubble or the James Webb Space Telescope, will be capable of watching. Competition for such observing time is fierce, but the scientific payoff could be unprecedented. By early December, 3I Atlas will re-emerge from solar glare, beginning its outbound trek. The reappearance will reopen ground-based observational campaigns, allowing astronomers to compare its pre- and post-perihelion states and assess what transformations the solar encounter may have wrought. On the 19th of December comes the moment of closest approach to Earth. 270 million kilometers, roughly twice the average Earth-Sun distance. Although far less dramatic than the sweeping apparitions of comets like Hale-Bopp or Hyakutake, this distance is close enough for detailed study, yet distant enough to pose no hazard. It offers a rare balance, safe passage for Earth, but a wealth of data for science. From that point forward, 3I Atlas will fade into the distance, outbound toward interstellar space once more. Whatever secrets it reveals during its fleeting time within our reach will remain humanity's only glimpse of this wanderer, a message delivered on the grand stage of cosmic clockwork. The Earth encounter marks the most critical moment in humanity's engagement with 3I Atlas. Not because of proximity alone, but because of what it symbolizes. Our best chance to test whether this wandering body carries more than dust and ice. If the comet was somehow connected to the WOW signal, if both were fragments of a vast interstellar communication design, then its closest approach to Earth in December of 2025 would offer the perfect observational window. At this juncture, the geometry aligns to minimize Doppler distortions. The reduced distance maximizes potential signal strength, and the object's position in the sky ensures nearly continuous monitoring by radio telescopes across the globe. This flyby is more than a search for whispers in the void. It is also an opportunity to test the object's motion against the unyielding predictions of celestial mechanics. Natural bodies obey gravity with machine-like precision, their orbits calculable years in advance. Should 3I Atlas deviate by even millimeters per second from its predicted course, the anomaly would speak volumes. Such subtle accelerations, if detected, could betray non-natural forces at work, perhaps propulsion systems or controlled maneuvers that no comet should possess. The transition from inbound to outbound trajectory, as the comet rounds the Sun and recedes, is precisely when such anomalies would most likely appear. By March 16, 2026, the visitor will encounter its final planetary guardian. On that date, it will pass within 0.36 astronomical units of Jupiter, a separation of about 54 million kilometers from the giant's cloud tops. Though still distant, this marks the closest approach to any major planet during its entire passage. The Jovian encounter excites both scientists and mission planners. NASA's Juno spacecraft, currently unraveling Jupiter's deep structure, could in theory be retasked to capture data on the interstellar traveler. Yet doing so would require significant fuel and risk to its primary mission. Similarly, Europe's JUICE spacecraft, arriving in the Jovian system around the same period, faces trade-offs between its scheduled program and any opportunistic detours toward Atlas. Even absent dedicated spacecraft maneuvers, the Jupiter passage promises scientific riches. Ground-based observatories will study the comet against Jupiter's vast and turbulent magnetosphere, probing how interstellar material responds to environments far harsher than Earth's. This moment also represents the last, best chance to study the object's coma and tail before they diminish, as solar heating wanes and Atlas begins its irreversible retreat into interstellar space. Once past Jupiter, the trajectory points outward, forever. Unlike comets bound to the Sun's gravity, which return in majestic cycles, 3I Atlas is a true exile. Its hyperbolic orbit ensures it will never come back. By late 2026, it will fade beyond the reach of our instruments, carrying its secrets back into the endless dark. Humanity's opportunity is singular, a campaign lasting barely 18 months, from its discovery in July of 2025 to its final observations the following winter. That campaign is unprecedented in scope. Across wavelengths from optical to infrared to radio, astronomers will chart its composition, activity, and evolution. They will record spectra, measure light curves, map tail structures, and monitor every fluctuation in its volatile release. Each stage of the journey, whether near Mars, at perihelion, near Earth, or by Jupiter, presents another moment to listen at 1420 MHz, the frequency etched into SETI's mythology by the wow signal. If signals repeat, even faintly, the interpretation of coincidence would falter. The choreography seems scripted, as though the universe itself has staged a performance for us. A radio whisper in 1977, followed decades later by a wandering comet from the same direction. Whether these notes compose a song or remain isolated beats of cosmic noise, we do not yet know, but as we watch and listen in the coming months, we remain heirs to that red-inked wow, the astonishment of realizing that perhaps, just perhaps, we are not the only players in this vast celestial dialogue. In the normally collegial world of astronomy, where debates typically unfold through carefully crafted journal articles or cordial exchanges at conferences, the arrival of 3i Atlas has sparked something closer to intellectual combat. Its unusual properties have become a flashpoint for deeper disagreements over how to interpret anomalies and what standards of evidence are necessary before invoking extraordinary explanations. The mainstream position, championed by NASA, the European Space Agency, and many leading observatories, is clear. 3i Atlas is a comet, an unusual one, but natural nonetheless. This conservative interpretation emphasizes the object's fundamentally cometary behavior. It develops a coma and tail. It responds predictably to solar heating. It follows a gravitational trajectory that celestial mechanics can account for with precision. According to this view, its chemical peculiarities, carbon dioxide dominance, nickel emission without iron, and seemingly exaggerated activity relative to its size are not signs of artificiality, but reflections of processes in stellar environments, unlike our own. Dr. Alan Fitzsimmons of Queen's University Belfast has articulated this perspective forcefully. He argues that we should expect exotic chemistry in interstellar objects, not be surprised by it. After all, humanity has studied only 3 confirmed interstellar visitors. Drawing conclusions from so small a sample, Fitzsimmons suggests, is like attempting to understand human diversity after meeting only 3 strangers. What looks abnormal compared to solar system comets may in fact be commonplace elsewhere, shaped by stars of different compositions, temperatures, or evolutionary paths. Supporting this view are refined observations from the Hubble Space Telescope, which have constrained the nucleus to no more than 5.6 kilometers across, and possibly as small as 300 meters. Such compact dimensions help explain its apparent overperformance. Smaller bodies present higher surface area to volume ratios, enabling more efficient volatile release when solar radiation heats them. In this light, vigorous outgassing is not miraculous but expected, yet not all are persuaded. Avi Loeb of Harvard University, well known for his earlier claim that Oumuamua might represent alien technology, has turned his attention to 3i Atlas. With characteristic boldness, he argues that the anomalies demand we keep technological hypotheses on the table. In blog posts, interviews, and preliminary papers, Loeb has pointed to the combination of unusual chemistry, unexpected activity, and precise orbital alignment with Sagittarius as evidence of what he calls the coincidence problem. The fact that 3i Atlas appeared during the 48th anniversary of the WOW signal and from the same general region of sky creates a probability deficit, he contends, that begs for explanation. He has suggested that both phenomena might be components of a probe mission designed to assess humanity's growing technological maturity. The response from the broader scientific community has been sharp. Jason Wright of Penn State University, a respected SETI researcher, stresses that extraordinary claims require extraordinary proof. To him, 3i Atlas falls far short. Yes, its properties are unusual, but unusual is not the same as impossible. For every anomaly observed, natural explanations remain plausible. Until astronomers detect unmistakable technosignatures, controlled maneuvers, structured radio transmissions, or materials that defy natural processes, conventional models must prevail. Loeb, Wright argues, is mistaking correlation for causation, reading intent into statistical happenstance. This divide captures more than a disagreement about one comet. It reveals fault lines in scientific culture between those who urge caution, demanding ironclad evidence before expanding the realm of possibility, and those who argue that anomalies are precisely where radical discoveries hide. For now, the consensus holds that 3I Atlas is natural, a strange but instructive emissary from beyond the solar system. Yet the debate itself underscores the profound stakes. In every outgassing plume and spectral anomaly, astronomers glimpse not only the chemistry of alien worlds but also the boundaries of their own willingness to imagine. Jason Wright and others in the mainstream camp point to several recent developments that strengthen the case for natural interpretations of 3I Atlas's behavior. Detailed thermal modeling, for instance, suggests that the object's striking carbon dioxide dominance could be a consequence of formation in the outer reaches of planetary systems orbiting stars hotter than our own Sunday. In such environments, volatile inventories might naturally skew toward carbon dioxide rather than water ice. The puzzling nickel emissions without corresponding iron detections, often cited as one of the strangest features, might also be less exotic than they appear. Certain mineral compositions or thermal processing pathways could preferentially release nickel into the coma, while delaying or suppressing iron's signature. Even the so-called overperformance, where the object's small nucleus seems to produce disproportionately vigorous activity, might be explained by structural factors, porous interiors, fractured surfaces, or layers of volatile rich material that maximize the efficiency of sublimation when sunlight strikes. The question of size has become especially contentious. Early estimates suggested a nucleus far larger than Hubble's latest constraints allow, fueling speculation about unusual densities or hidden internal architectures. But as observations improved, most results converged on smaller dimensions, with an upper limit of about 5.6 kilometers, and some analyses favoring diameters closer to 300 meters. This shift brings the object more firmly into line with conventional comet expectations. Dr. Maria Womack of the University of South Florida, who leads several of the ongoing observation campaigns, has repeatedly stressed the need for patience. She warns against drawing sweeping conclusions from preliminary data, pointing out that science advances not through sensational claims but through careful, cumulative analysis. We need months or years of study before reliable conclusions can be made, she notes, criticizing media outlets and bloggers who proclaim certainty on the basis of incomplete information. The controversy surrounding 3I Atlas thus extends beyond the object itself into broader debates about scientific culture. Some researchers fear that premature speculation about alien technology risks, damaging astronomy's credibility and undermining efforts to secure funding for legitimate SETI research. Others argue that reflexive conservatism may blind us to genuine breakthroughs, that ignoring unconventional possibilities out of fear of ridicule risks missing discoveries that could fundamentally reshape our place in the cosmos. These disagreements reveal deeper philosophical divides. One side insists that all natural explanations must be exhausted before exotic ones are entertained, citing history, pulsars, gamma-ray bursts, and fast radio bursts all looked artificial when first discovered, only to reveal natural mechanisms. The other side insists that paradigm-shifting discoveries often come from daring to consider radical possibilities, pointing out that SETI itself began when visionary scientists proposed taking seriously the idea that radio signals might reveal alien intelligence. Complicating matters further is media coverage that often blurs the line between peer-reviewed findings and speculative commentary. Headlines alternately proclaim 3I Atlas to be an alien probe or an entirely normal comet, leaving the public confused about what astronomers actually know. This distortion shapes public opinion and may influence the allocation of resources for future research. In response, professional organizations have begun issuing guidelines for responsible communication. The International Astronomical Union urges scientists to present multiple hypotheses rather than leaning into sensationalism, while SETI institutions emphasize rigorous verification procedures before announcing claims of extraterrestrial origin. Meanwhile, the data stream grows. Spectroscopic studies continue to show chemical signatures that defy easy categorization, while photometric measurements document fluctuations in brightness and color that may indicate surface patchiness or complex rotation. Perhaps most notable are coordinated searches for radio emissions undertaken by facilities like the Very Large Array and the Green Bank Telescope. These represent the first systematic efforts to listen for signals from an interstellar visitor. The silence so far is ambiguous fuel for both camps. Skeptics see it as further proof of natural origin surely an alien probe would transmit. Advocates counter that advanced technologies might communicate only under specific conditions, or in ways we have not yet learned to detect. As 3I Atlas approaches its crucial encounters with Mars and perihelion, the stakes intensify. If unmistakable technosignatures emerge, controlled maneuvers, structured radio emissions, or materials beyond natural capacity, the current debates will be remembered as the hesitant first steps toward a transformative discovery. If the object continues to behave like a comet, albeit one from a foreign stellar nursery, then the episode will stand as a lesson in scientific humility, a reminder of the dangers of both overzealous speculation and excessive skepticism. In either case, 3I Atlas has already achieved something remarkable. It has forced astronomy to grapple openly with the boundaries of evidence and the role of imagination. It has reminded us that anomalies are both peril and opportunity, capable of misleading but also capable of revolutionizing our understanding. The next few months will decide whether this story becomes a footnote in the history of mistaken anomalies or the opening chapter of a much larger cosmic dialogue. The human brain is a pattern-making machine, evolved to weave meaning from the noise of existence. For our ancestors, this instinct was not a luxury, but a survival tool. The ability to distinguish a predator's rustle in the grass from the random hiss of wind often meant the difference between life and death. In our modern age, this same evolutionary gift serves us in a different arena, interpreting the universe. Yet when the canvas is the cosmos, pattern seeking can mislead us, conjuring connections where none exist, turning coincidence into conspiracy. The apparent relationship between the WOW signal and 3I Atlas illustrates this tension perfectly. Two anomalies, separated by nearly 50 years, both traced back towards Sagittarius. The symmetry of this pairing feels almost scripted, as though the universe were whispering a secret. Our minds resist dismissing such alignment as statistical accident. Yet, examined dispassionately, the evidence begins to fray. The WOW signal's refined coordinates still cover a patch of sky, about 8 arc-minutes across. 3I Atlas's radiant, mapped with its own uncertainty, lies several degrees away. In cosmic terms, this offset translates into millions of light-years of difference, hardly the pinpoint accuracy we might expect from a deliberate communication. The temporal alignment is equally slippery. If 3I Atlas was expelled from its birth system millions or billions of years ago, its arrival now, during humanity's first radio centuries, might seem miraculous. But without knowing its true age or origin, we cannot determine whether its timing is deliberate targeting or simple happenstance. Temporal coincidence, like directional overlap, teases more than it clarifies. The Sagittarius connection, far from resolving the mystery, complicates it further. This constellation frames the galactic center, the noisiest and most energetic sector of the Milky Way. Pulsars, magnetars, supernova remnants, and dense molecular clouds fill the region with a flood of radio signals. Anomalies from this direction may say more about the inherent chaos of the galactic hub than about technological civilizations. Statistical reasoning provides little comfort. With just one unexplained radio burst of the WOW signal's magnitude and only 3 confirmed interstellar visitors, humanity's dataset is laughably small. We cannot yet determine whether such events are common or rare, random or clustered. A sample size of 2 cannot prove connection, but it cannot disprove it either. The maser hypothesis for the WOW signal further muddies the waters. Many astronomers now favor the idea that the signal was not artificial at all, but a natural hydrogen maser triggered by some violent astrophysical event. If so, any attempt to link it to 3I Atlas collapses. We would then be dealing with 2 separate natural phenomena that happened, by chance, to arise from roughly the same direction. Yet dismissing the coincidence outright requires its own leap of faith, because the odds of such alignment, however small, nag at the imagination. Here lies the paradox. The universe contains an estimated 2 trillion galaxies, each with hundreds of billions of stars, each with countless planets. If even a tiny fraction of those worlds harbor advanced life, then the galaxy may be alive with civilizations capable of sending signals or dispatching probes. From this broader perspective, the connection between the WOW signal and 3I Atlas might not be mere accident. It could represent our first glimpse of a hidden galactic network, a whisper of infrastructure spanning the stars. Perhaps the original transmission was a beacon, and the interstellar visitor a probe sent to investigate planets that showed signs of technological awakening. This narrative, however speculative, would elegantly explain both the timing of 3I Atlas's arrival and its approach from the same region of sky. Testing such a hypothesis requires evidence that moves beyond coincidence. The most direct would be radio emissions from 3I Atlas itself, ideally near the hydrogen line where the WOW signal once flared. Structured transmissions, deliberate modulations, or bursts, timed to its planetary flybys, would tilt the scales toward artificial origin. Conversely, continued silence would strengthen the case for coincidence. For now, the question remains unsettled. We are left navigating the borderland between imagination and observation, between our brain's hunger for patterns and the universe's indifference. Whether linked or not, the WOW signal and 3I Atlas together remind us of the fragility of certainty when we gaze into the cosmic dark. If 3I Atlas were truly an alien probe sent in response to the WOW signal, then communication either with Earth directly or with its creators would be an expectation. Its current silence in the radio spectrum, however, suggests either a natural object behaving like a comet or, in the more speculative view, a technological artifact operating under deliberate stealth. The absence of detectable transmissions underscores the immense difficulty of proving artificial origin. Physical properties provide another set of tests. A genuine technological artifact should reveal material or structural traits inconsistent with natural bodies. Controlled course corrections, surface features that suggest machining, non-gravitational accelerations that cannot be explained by outgassing, or thermal signatures inconsistent with simple sublimation, All of these would point to something beyond nature. So far, 3I Atlas has conformed to expectations of a comet, a coma and tail forming under solar heating, volatile release matching predictable energy input, and a purely gravitational trajectory. Astronomy's history reminds us of the dangers of jumping too quickly to extraordinary explanations. Pulsars, discovered in the 1960s, were initially nicknamed LGM for Little Green Men, before being understood as rotating neutron stars. Fast radio bursts, once suspected to be artificial, are now linked to extreme astrophysical events. Each anomaly broadened our understanding of natural processes. This history does not rule out the possibility of alien technology, it simply raises the bar. Extraordinary claims demand extraordinary evidence. The connection hypothesis, linking 3I Atlas and the WOW signal, is appealing in narrative terms. It provides a framework for organizing questions, generating predictions, and motivating intensive campaigns of observation, but it also carries risks. Confirmation bias can tempt researchers to interpret ambiguous data as support for their preferred explanation. Every unusual spectral line, every fluctuation in brightness, and every detected radio anomaly will be scrutinized for signs of intent. The scientific challenge is to weigh such findings against equally rigorous natural explanations. The next months will be decisive. As the object passes near Mars, rounds the Sun at perihelion, and makes its closest approach to Earth, we will have opportunities to search for radio emissions, track its trajectory with exquisite precision, and study its chemistry under maximum solar stress. If evidence emerges of artificial origin, the correlation with the WOW signal would transform from coincidence into discovery of epochal significance. If not, we will still learn invaluable lessons about the chemistry of interstellar comets, about how planetary systems form in alien environments, and about our own psychological tendency to see patterns in the stars. Either way, the process reflects science at its best. We form hypotheses, we design tests, and we remain willing to revise our conclusions as new data arrives. With only one unexplained radio signal and 3 interstellar visitors in our history, every apparent correlation deserves careful, methodical attention. To dismiss them too soon would be to risk overlooking discoveries that could redefine humanity's understanding of its cosmic neighborhood and its place within it. In the realm of speculative science, few ideas ignite the imagination quite like the suggestion that we may be witnessing a coordinated interstellar communication effort. Imagine a conversation conducted not only through fleeting bursts of radio energy, but also through the deliberate movement of objects across the vastness of space. This is the essence of what some researchers have dubbed the message in motion hypothesis, a bold framework that seeks to link two of astronomy's most tantalizing enigmas: the WOW signal of 1977 and the interstellar object now known as 3I Atlas. According to this scenario, the WOW signal functioned as an announcement, an unmistakable attention getter broadcast across the hydrogen line, the universal hailing frequency of the cosmos. Its narrow bandwidth and extraordinary intensity would have distinguished it from the cacophony of natural radio sources, ensuring that any civilization with even rudimentary radio astronomy would take notice. The signal's one-time appearance, long regarded as its greatest weakness, becomes in this view part of the design, a single, deliberate pulse meant to minimize ambiguity while avoiding the energy demands of a continuous beacon. The second stage of the message, according to this hypothesis, is far more audacious. Rather than relying on additional radio transmissions, which might be missed, distorted, or lost amid cosmic noise, the originating civilization could have dispatched a physical emissary. 3I Atlas, in this framework, is not simply a comet, but a disguised technological artifact, its unusual properties serving as camouflage for advanced systems hidden within. The apparent 48-year interval between the WOW signal and the comet's arrival would then make perfect sense. Radio waves, traveling at light speed, could reach Earth in years or decades from a nearby stellar neighborhood. A physical probe, even one equipped with advanced propulsion, would require decades more to cross interstellar distances. This timing suggests a likely origin within 10 to 30 light-years, close enough for two-way communication yet distant enough to demand significant travel time. Such a hypothesis elegantly ties together anomalies that otherwise remain puzzling. The WOW signal's silence after its initial detection becomes a deliberate design choice rather than a failure of follow-up searches. The odd chemistry of 3I Atlas, its carbon dioxide-rich emissions, its selective nickel without iron signature, its vigorous activity, despite modest size, might represent engineered camouflage rather than natural composition. Even its retrograde, low-inclination orbit could be interpreted not as coincidence, but as evidence of controlled trajectory adjustments. The strength of this idea lies not merely in its narrative power, but in its testable predictions. If 3I Atlas is truly a probe, several observational signatures should reveal its nature during its solar system passage. The first and most obvious would be radio emissions. Structured signals, particularly those tied to harmonics of the hydrogen line or mathematically significant frequencies, would provide compelling evidence. Modulation patterns, frequency drifts compensating for motion, or repeated bursts timed with planetary encounters would further strengthen the case. A second line of evidence would involve motion. Natural comets display subtle non-gravitational accelerations due to asymmetric outgassing, but these accelerations follow predictable patterns. Should 3I Atlas execute maneuvers inconsistent with sublimation physics, precise course corrections, sudden changes in velocity, or thrust signatures, it would cross the threshold into the artificial. Third, detailed spectroscopic studies could uncover impossible materials. Industrial alloys, non-terrestrial isotopic ratios, or compounds unknown in natural astrophysical environments would serve as smoking guns. The puzzling nickel without iron signature already observed may represent an early clue in this direction. Finally, thermal observations might betray hidden systems. Infrared emissions inconsistent with passive solar heating, especially if variable in structured patterns, could reveal internal power sources, active cooling systems, or even propulsion technologies. The message in motion hypothesis, while speculative, forces us to sharpen our methods. It challenges astronomers to look beyond conventional explanations without abandoning scientific rigor. Perhaps 3I Atlas will prove to be nothing more than an exotic comet, a natural wanderer shaped in alien environments. But if its journey through our solar system yields even a hint of artificiality, the implications would be staggering. It would mean that the WOW signal was not an isolated enigma, but the opening chapter in a conversation spanning light years, a conversation we are only now beginning to recognize. However, each of these potential tests faces formidable challenges and equally plausible alternative explanations. Radio emissions, for instance, are not in themselves proof of artificiality. While rare, comets have been observed producing natural radio signatures, usually generated when solar wind particles interact with their expanding comet. These emissions can create narrowband features that, at first glance, might resemble artificial signals. Distinguishing between plasma interactions and deliberate transmissions requires extremely careful analysis. Signal stability, modulation patterns, and polarization characteristics all become critical markers. Without such precision, even genuine anomalies risk being dismissed as noise in a universe filled with natural radio sources. Non-gravitational accelerations present similar difficulties. The controversy surrounding Oumuamua demonstrated just how complex these analyses can be. Some researchers argued its slight deviation from a purely gravitational trajectory required exotic explanations, perhaps even propulsion. Others countered with models of asymmetric outgassing, showing that natural processes might mimic the same effect. In the case of 3I Atlas, its vigorous cometary activity could actually obscure subtle measurements, providing obvious natural mechanisms for minor trajectory shifts. Distinguishing between volatile jets and controlled maneuvers may prove nearly impossible without direct spacecraft observations. Material composition anomalies, too, must be handled with caution. The carbon dioxide dominance, or the nickel without iron emission lines, may look exotic to us, but our sample of interstellar objects remains minuscule. Planetary systems forming around stars with different masses, metallicities, or evolutionary histories might naturally produce chemical abundances that diverge sharply from solar system norms. What strikes us as anomalous may be perfectly ordinary elsewhere in the galaxy. Thermal behavior is no less tricky. Cometary nuclei are notoriously complex, with porous interiors, stratified layers of volatiles, and rotational cycles that create seasonal effects. Localized heating can cause sudden outbursts or asymmetric sublimation that complicate thermal models. Detecting heat signatures inconsistent with pure solar illumination would require extraordinarily precise measurements. Even then, distinguishing between natural heterogeneity and artificial power sources remains an interpretive challenge. Beyond these technical obstacles, the message in motion hypothesis faces broader logical critiques. If an advanced civilization sought to communicate, why choose such an elaborate and time-consuming strategy? Radio transmissions allow for near-instantaneous contact across interstellar distances. Physical probes, by contrast, require decades or centuries to arrive, and the risks of failure multiply across such long voyages. The resource investment would be immense. Disguising a probe as a comet adds another layer of complexity. If the intent were open communication, why not design the object to appear unmistakably artificial, eliminating ambiguity and ensuring recognition? These objections do not invalidate the hypothesis, but they do highlight its extraordinary demands. Perhaps alien communication strategies follow logics we cannot yet grasp. A probe might carry physical samples, advanced instruments, or even biological material, things that radio cannot transmit. Camouflage could reflect caution, a desire to observe without prematurely revealing intent. It might represent a universal survival strategy, a way of testing the waters before risking exposure to potentially hostile intelligence. The hypothesis also forces us to wrestle with deeper philosophical questions. What kind of civilization would plan missions on timescales of decades or centuries? How would they coordinate across interstellar distances? What motives scientific curiosity, strategic monitoring, or a desire for eventual contact would justify such a monumental effort? These questions remain firmly speculative, but they remind us that even considering such ideas stretches our imagination about what intelligence and technology could become. As 3I Atlas approaches its decisive encounters with Mars and the Sun, the message in motion hypothesis faces its most rigorous tests. Should the object display unambiguous artificial signatures, structured emissions, precise maneuvers, or impossible material properties, then this framework would shift overnight from speculation to discovery. If instead, the data continue to align with natural cometary interpretations, then the hypothesis will join the long history of imaginative but incorrect attempts to explain cosmic anomalies. Either outcome holds immense value. In one case, humanity would confirm the existence of alien technology. In the other, we would refine our methods, sharpen our skepticism, and learn to distinguish genuine discoveries from the illusions created by our own pattern-seeking minds. That, ultimately, is the essence of science. Bold hypotheses, rigorously tested, with conclusions shaped not by desire but by evidence. The message in motion hypothesis may or may not survive this trial, but in daring to test it, we exemplify the scientific method at its most adventurous and its most valuable. In the grand symphony of cosmic radio emissions that surrounds our planet every moment of every day, the act of listening for artificial signals requires both technological sophistication and profound patience. As 3I, Atlas continues its journey through our solar system, radio astronomers around the world are preparing for what may be the most intensive SETI listening campaign in history, a coordinated effort to detect any transmissions that might emanate from our mysterious interstellar visitor. The listening strategy focuses on the most promising observational windows, times when geometry, proximity, and gravitational dynamics create optimal conditions for signal detection. The Mars flyby in early October represents the first critical opportunity as 3I Atlas passes within 30 million kilometers of the red planet. If the object were programmed to respond to planetary encounters perhaps triggered by gravitational fields or magnetic environments, this would be the moment for initial activation. The perihelion passage in late October offers even more dramatic possibilities. As 3I Atlas rounds the Sun at its closest approach, solar heating reaches maximum intensity, potentially triggering changes in the object's behavior or revealing hidden capabilities. The intense radiation environment might activate dormant systems, power up communication arrays, or trigger programmed responses designed to announce the probe's presence to any observing civilizations. But perhaps the most significant window occurs during 3I Atlas's closest approach to Earth in mid-December. At a distance of approximately 270 million kilometers, any signals originating from the object would reach maximum strength while minimizing Doppler effects that could complicate frequency analysis. The geometry would allow continuous monitoring by radio telescopes worldwide, as Earth's rotation sweeps different facilities into optimal viewing positions. The search frequencies focus primarily on the waterhole region between 1020 and 1670 MHz, with special attention to the exact frequency where the WOW signal appeared 4 decades ago. But modern SETI protocols recognize that alien communication systems might operate according to principles we do not yet understand. So the searches will span much broader spectral ranges, from low-frequency radio waves up through microwave and millimeter wavelengths. The Breakthrough Listen project, funded by Russian entrepreneur Yuri Milner, has already begun dedicating substantial observing time to 3I Atlas monitoring. Their global network of radio telescopes includes the Green Bank Telescope in West Virginia, the Parkes Observatory in Australia, and the Meerkat Array in South Africa. These facilities offer complementary capabilities, different frequency ranges, observing geometries, and sensitivity levels that together provide comprehensive coverage of potential signal characteristics. China's 500-meter aperture spherical telescope, the world's largest single-dish radio telescope, has also joined the campaign. FAST's enormous collecting area makes it particularly sensitive to weak signals, while its southern latitude provides coverage of sky regions inaccessible to northern hemisphere facilities. The telescope's recent commissioning for SETI observations adds unprecedented sensitivity to the search effort, potentially enabling the detection of signals billions of times weaker than those required to be heard by the original Big Ear telescope that recorded the WOW signal in 1977. The technical challenges of detecting artificial signals from 3I Atlas extend far beyond simple sensitivity requirements. Any genuine extraterrestrial transmission would likely display characteristics that distinguish it from natural radio sources, complex modulation patterns, precise frequency stability, or structured information content. Modern machine learning algorithms can identify such signatures even when embedded in cosmic noise, but they must be carefully calibrated to avoid false positives from human satellites, terrestrial interference, or natural astrophysical phenomena. Doppler analysis presents particular opportunities and challenges. 3I Atlas's rapid motion through our solar system creates predictable frequency shifts for any signals originating from the object. Natural sources would display Doppler patterns that precisely match the object's trajectory. Artificial transmissions, however, might show additional frequency drifts designed to compensate for relative motion or even encode information within the changing signal characteristics. Detecting such signatures would provide compelling evidence of technological origin. As the world's most powerful observatories turn their ears to the sky in the coming months, the search for transmissions from 3I Atlas will stand as one of the most ambitious listening campaigns in human history. Whether the outcome is cosmic silence or the first confirmed message from beyond Earth, the effort itself embodies the essence of SETI, the willingness to listen patiently, rigorously, and open-mindedly for voices that may already be speaking across the stars. Polarization measurements add another dimension to the search strategy. Radio waves carry information in their electric field orientations, and artificial transmissions might display polarization signatures that would be difficult or impossible for natural processes to reproduce. Circular polarization, rapid orientation shifts, or structured polarization patterns could serve as strong indicators of technological origin. The campaign does not stop at radio. Searches extend into optical and infrared regimes, scanning for pulsed laser communications, artificial thermal emissions, or modulated reflections of sunlight that might accompany radio transmissions. These multi-wavelength approaches expand the range of possibilities while providing redundant confirmation if any candidate signals appear. Citizen science also plays an important role. Projects like SETI at home have already demonstrated the power of distributed computing to analyze vast archives of radio data. Today, amateur astronomers equipped with sophisticated backyard observatories can contribute real observations. The 3I Atlas campaign has been structured to welcome both professional and amateur participation, creating what may be the most inclusive search for extraterrestrial intelligence ever attempted. Time domain analysis adds yet another layer. Instead of focusing only on continuous transmissions, researchers are monitoring for brief bursts, repeating pulses, or signals that appear only during particular alignments. Such intermittent broadcasts would conserve transmitter power while remaining easier to distinguish from cosmic background noise. The human dimension of this search deserves equal attention. If an artificial signal were detected, the discovery would trigger carefully defined verification and notification protocols established by the international SETI community. Independent confirmation by multiple facilities would be mandatory before any public announcement, followed by exhaustive efforts to rule out terrestrial interference or exotic natural explanations. Negative results, however, would be no less important. The absence of detectable transmissions would help define upper limits on the power and sophistication of any hypothetical alien technology. Each null result narrows the possibilities and improves our understanding of the cosmic communication landscape. Equally significant, the 3 Atlas listening campaign functions as a proving ground for the next generation of SETI methodology. New algorithms, data pipelines, and global coordination protocols developed during this monitoring effort will establish benchmarks for how humanity responds to anomalous discoveries in the future. The campaign is effectively a dress rehearsal for contact, ensuring that when the moment finally comes, whether in years or centuries, we will have the procedures and experience necessary to respond coherently. The educational impact is just as profound. Students around the world are being recruited into real data analysis projects, while outreach initiatives bring the public into the process. The campaign illustrates science in action, showing how bold hypotheses are tested with rigorous methods and international collaboration. As radio telescopes across the globe turn toward 3I Atlas during its passage, they carry with them the hopes of our species. The simple act of listening represents humanity at its most optimistic, investing effort and resources on the chance that someone, somewhere, might be reaching out. Whether the cosmos answers with silence or with the first unmistakable sign of technology beyond Earth, the campaign will mark a milestone in our history. We are no longer passive observers of the universe. By listening deliberately, carefully, and with unprecedented sensitivity, we declare our readiness to join the cosmic conversation if indeed anyone else is speaking. Beyond the immediate mysteries surrounding 3I Atlas and its potential connection to the WOW signal lies a broader transformation in our understanding of the cosmic environment we inhabit. This interstellar visitor represents far more than a single anomalous object. It embodies our species' growing recognition that the universe is dynamic, interconnected, and filled with wanderers carrying silent stories from worlds we may never directly observe. The scientific value of studying interstellar objects extends far beyond the possibility of alien technology or communication. These visitors address fundamental questions about how planetary systems form, evolve, and scatter material into the galaxy. Every comet, asteroid, or fragment ejected from another star system preserves within its chemistry and structure the fossil record of processes that took place billions of years ago around alien suns. They are time capsules drifting between the stars, each containing clues about stellar environments, protoplanetary disks, and the early conditions that shape the worlds we may never see. 3I Atlas's unusual carbon dioxide to water ratio exemplifies this scientific treasure. In our own solar system, the abundance patterns of volatiles reflect the temperature gradients, pressure distributions, and chemical compositions that existed when the sun was young and surrounded by a disk of gas and dust. Most comets here show water as the dominant component, with carbon dioxide present but secondary. Yet 3I Atlas appears to invert this balance, presenting a carbon dioxide to water ratio of nearly 8:1. Such chemistry suggests formation in an environment dramatically different from our own, perhaps a hotter or more massive star, or one with elemental abundances unlike those we are accustomed to. This inverted chemistry carries profound implications. It demonstrates that the recipe for planetary building blocks varies widely across the galaxy, and that what seems anomalous to us might be entirely normal elsewhere. The strange detection of nickel emission lines without corresponding iron offers another window into cosmic diversity. These two metals are normally paired, forged together in stellar interiors, and deposited side by side in planetary material. Their apparent separation in 3I Atlas suggests unusual processes, perhaps novel mineral phases, thermal conditions that release one element but not the other, or entirely unfamiliar chemical pathways that remain hidden to us. Understanding this selective emission could reveal not just new insights into cometary behavior, but also information about the environments in which such objects were born. The observational campaign that has risen around 3 Atlas is unprecedented. Humanity now possesses tools capable of wringing maximum information from such a fleeting visitor. The James Webb Space Telescope, with its unparalleled infrared sensitivity, dissects faint molecular emissions and reveals volatile inventories invisible to earlier instruments. The Hubble Space Telescope contributes high-resolution imaging, constraining the nucleus's size, shape, and rotation, crucial details for models of internal structure. Ground-based facilities add continuous monitoring, documenting how the coma expands and the tail evolves as solar heating intensifies. From Chile's Atacama Desert to observatories scattered across the globe, astronomers are watching in concert, creating a multi-wavelength portrait of an interstellar traveler. This collaboration represents a new paradigm in astronomy, one focused on seizing short-lived opportunities with every available instrument. Stars and galaxies evolve too slowly for such urgency, but interstellar visitors sweep through only once before disappearing forever. Each object provides a brief window into alien planetary histories, and every measurement becomes part of a growing archive of galactic archaeology. The lessons learned from 3I Atlas will inform how we study future interstellar objects, and those objects are coming. The Legacy Survey of Space and Time, soon to begin operations, is expected to discover dozens or even hundreds of these wanderers each decade. Our tiny collection of 3 confirmed interstellar visitors will become a population large enough to reveal patterns. We will begin to learn what chemical signatures dominate among extrasolar comets, which stellar environments eject the most debris, and how often true anomalies appear within the broader statistical distribution. Citizen scientists are also contributing to this unfolding story. Amateur astronomers, with advanced telescopes, monitor brightness changes, track positional shifts, and document how the coma and tail evolve over weeks. Projects like the Interstellar Citizen Science Campaign collect data from dozens of locations worldwide, providing coverage no single professional observatory could match. These contributions not only increase the total data available, but also help confirm observations and identify possible systematic errors. The story of 3I Atlas is thus not only one of professional discovery, but also of collective human curiosity reaching outward together. The implications extend into astrobiology and the search for life beyond Earth. Interstellar comets demonstrate that material is constantly exchanged between planetary systems. Fragments carrying water, organic molecules, and other chemical ingredients drift through the galaxy, sometimes passing through foreign solar systems. This raises the possibility that the seeds of life, or at least its chemical precursors, might travel between stars, linking planetary systems in ways we are only beginning to grasp. If life on Earth was shaped in part by such galactic exchanges, then studying interstellar visitors like 3I Atlas is not merely about distant stars, it is about our own origins. Whether 3I Atlas ultimately proves to be nothing more than a natural comet or something profoundly more extraordinary, it reminds us of the deep interconnectedness of the cosmos. Its chemistry challenges our expectations, its trajectory tests our detection capabilities, and its fleeting presence demands urgency and observation. Above all, it underscores that our solar system is not an isolated island, but part of a wider galactic ocean, where material flows freely, carrying with it the histories of other stars. Every interstellar visitor expands that awareness, transforming the universe from a distant abstraction into an intimate network of connections, and reminding us that even in the vast silence between the stars, there are always new stories arriving at our doorstep. While 3I Atlas shows no indications of biological activity, it invites speculation about what future interstellar visitors might carry. Some may transport organic compounds, complex molecules, or even dormant microorganisms preserved from their native planetary systems. If such evidence were ever detected, it would represent a profound discovery, direct proof that life's chemical seeds are not unique to our solar system. The possibility of panspermia, the natural transfer of life between planetary systems, becomes a central theme here. Should microorganisms prove capable of surviving millions of years in the harsh vacuum and radiation of interstellar space, objects like 3I Atlas could serve as cosmic couriers, distributing biology across unimaginable distances. The discovery of preserved life in such a body would not simply broaden our biological catalogue, it would redefine our understanding of life's place and prevalence in the cosmos. Even absent biological cargo, interstellar visitors remain invaluable. They preserve chemical records of the environments in which they formed, archives of stellar nucleosynthesis, supernova enrichment, and heavy element distribution from epochs that may no longer exist. Some may have been ejected billions of years ago, carrying with them a frozen snapshot of galactic history. In this sense, they are time capsules, offering insights into the processes that shaped stars, planets, and the broader structure of the Milky Way. The practical benefits of studying these objects ripple outward through astronomy. The push to identify and track fast-moving interstellar intruders has spurred new detection algorithms, which also enhance our capacity to catalogue potentially hazardous asteroids closer to home. Advances in spectroscopic techniques, driven by the need to decipher alien chemistries, improve our understanding of native comets and asteroids. International coordination, refined by the urgency of brief observational windows, strengthens the global community's ability to respond rapidly to time-sensitive discoveries. Perhaps most important, though, is the way interstellar objects challenge our intellectual frameworks. 3I Atlas, with its anomalies of chemistry and activity, reminds us that the universe is not bound by our expectations. Each surprising measurement is a lesson in humility, an invitation to expand our models and admit how much we do not yet know. As it arcs toward its encounters with Mars, the Sun, and Earth, 3I Atlas carries more than frozen gases and dust. It carries the accumulated curiosity of a species determined to understand its place in the universe. Every observation, every spectrum, every light curve, every fleeting image adds to a shared record of cosmic engagement. Whether this visitor proves to be merely an exotic comet or something more astonishing, its passage marks a milestone in humanity's growing cosmic maturity. We are no longer passive watchers of distant wonders, but active participants in a universe that delivers emissaries from other star systems, each one whispering secrets from the vast dark between suns. The larger truth emerging is of a galaxy far more dynamic and interconnected than our ancestors could have imagined, a place where matter, and perhaps even life, travels between stars, where no world is truly isolated, and where the next arrival could overturn everything we think we know about existence itself. As we reach the end of our journey through the mysteries surrounding 3I Atlas and its potential connection to the WOW signal, we stand at a remarkable juncture in human history. Never before have we possessed such sophisticated tools for investigating cosmic anomalies. Never before have we been so well positioned to detect signs of extraterrestrial intelligence, and never before have we faced such tantalizing possibilities for discovering that we are not alone in the universe. The story we have traced, beginning on that fateful night in August 1977, when Jerry Eman first scrawled, "Wow," across a computer printout, through decades of follow-up searches and theoretical speculation, to the arrival of our mysterious interstellar visitor in 2025, represents more than just a chronicle of unexplained phenomena. It embodies humanity's persistent refusal to accept easy answers, our willingness to pursue questions even when they lead into uncomfortable uncertainties, and our growing confidence in our ability to explore the cosmos with scientific rigor. Whether the correlation between the WOW signal and 3I Atlas ultimately proves meaningful or coincidental, both phenomena have already succeeded in advancing our understanding of the universe. The original radio transmission demonstrated that our instruments were capable of detecting powerful signals from interstellar distances, validating search strategies and inspiring generations of SETI researchers. It established benchmarks for evidence evaluation that continue to guide our response to anomalous discoveries. 3I Atlas, regardless of its ultimate nature, has provided unprecedented opportunities to study authentic interstellar material with modern analytical techniques. Every spectrum collected, every image captured, and every measurement recorded contributes to our understanding of planetary system formation beyond our local cosmic neighborhood. The object has forced us to expand our models of cometary behavior, confront our assumptions about what constitutes normal chemistry, and develop new methodologies for investigating time-limited phenomena. Perhaps most importantly, both mysteries have demonstrated the power of maintaining epistemic humility, the recognition that our current understanding represents only a small fraction of cosmic reality. The universe continues to surprise us with phenomena that challenge our theories, stretch our imaginations, and remind us that the unknown vastly exceeds the known. The scientific process that has guided our investigation of these mysteries exemplifies humanity's most noble intellectual traditions. We observe carefully, measure precisely, propose hypotheses, test predictions, and remain prepared to revise our conclusions based on new evidence. We distinguish between speculation and fact, label our assumptions clearly, and acknowledge the limitations of our knowledge. This methodological rigor becomes particularly crucial when investigating phenomena that might represent contact with extraterrestrial intelligence. The potential implications are so profound that extraordinary care must be taken to avoid both premature conclusions and premature dismissals. As 3I Atlas approaches its critical encounters with Mars, the Sun, and Earth over the coming months, radio telescopes around the world will be listening with unprecedented sensitivity for any signals that might emanate from our interstellar visitor. These searches represent more than attempts to validate specific hypotheses. They embody humanity's commitment to remaining alert for messages from beyond our world. The listening campaigns planned for 3I Atlas's passage also serve as preparations for future opportunities. The techniques, protocols, and international coordination mechanisms being developed during this investigation will establish standards for responding to other anomalous objects or signals. We are, in effect, building the infrastructure for cosmic communication, creating systems capable of detecting, verifying, and responding to potential messages from extraterrestrial civilizations. The educational and inspirational aspects of this investigation extend far beyond the scientific community. Students around the world are participating in data analysis projects. Citizen scientists are contributing their own observations through amateur telescopes, and the general public is engaging with questions about our cosmic significance in ways that transcend traditional boundaries between science and philosophy. The search for extraterrestrial intelligence has become a genuinely global, species-wide endeavor. Looking forward, the coming decades promise revolutionary advances in our ability to investigate cosmic mysteries. The legacy survey of space and time will likely discover hundreds or even thousands of additional interstellar visitors, transforming our current sample of 3 objects into a statistical population that can reveal broader patterns about planetary system formation throughout the galaxy. Next-generation radio telescopes, including the Square Kilometre Array, will achieve sensitivities far beyond current capabilities, enabling the detection of much weaker signals across wider frequency ranges. The James Webb Space Telescope and its successors will provide unprecedented views of exoplanet atmospheres, potentially revealing biosignatures or even technosignatures in the chemical compositions of distant worlds. Advanced interferometry techniques will allow direct imaging of Earth-sized planets around nearby stars, bringing us closer to answering fundamental questions about the prevalence of life. Yet perhaps the most significant development will be the maturation of our species' cosmic perspective. Each investigation of anomalous phenomena, each null result in SETI searches, and each discovery of exotic but natural objects contributes to our growing understanding of what is possible, what is probable, and what remains mysterious. The correlation between the WOW, signal, and 3I Atlas, whether it ultimately proves meaningful or coincidental, has already served a valuable purpose. It has sharpened our awareness of the types of evidence we would need to establish genuine connections between apparently separate phenomena. It has highlighted the importance of long-term monitoring, of international collaboration, and of keeping speculation balanced with scientific discipline. Waiting for the next wow means living in a state of readiness, cultivating both patience and curiosity. It means accepting that the universe may reveal its secrets only sporadically, through fleeting signals and brief interstellar visits. It also means recognizing that every anomaly, whether ultimately mundane or extraordinary, represents another step forward in humanity's cosmic education. The unknown remains vast, but with every new mystery we investigate, our species grows more prepared for the moment when the signal repeats, the probe reveals itself, or the universe finally answers back. It has forced us to develop more rigorous statistical frameworks for evaluating cosmic coincidences, more sophisticated techniques for analyzing anomalous objects, and more careful protocols for distinguishing between natural and artificial signatures. These methodological advances will prove invaluable when we encounter future mysteries, and we can be certain that such mysteries will continue to emerge as our observational capabilities expand. The universe has a long history of surprising us with phenomena we never anticipated. Pulsars were once mistaken for artificial beacons before their true nature as rapidly spinning neutron stars was revealed. Quasars baffled astronomers until they were recognized as the luminous hearts of distant galaxies powered by supermassive black holes. More recently, the concepts of dark matter and dark energy have rewritten our understanding of the cosmos, showing us that most of the universe is composed of entities we can neither see nor touch directly. Each discovery has required us to expand our conceptual frameworks and revise our understanding of physical reality. The search for extraterrestrial intelligence represents perhaps the ultimate extension of this scientific adventure. Unlike other astronomical investigations that focus on physical processes or cosmic structures, SETI seeks phenomena that may have been deliberately created by beings with intentions, capabilities, and motivations we can scarcely imagine. This search compels us to confront profound questions about the nature of intelligence itself, the likelihood of technological civilizations, and the strategies such civilizations might employ to communicate across interstellar distances. It forces us to reflect on our assumptions, what alien intelligence might look like, how it might behave, and what traces of its existence it might leave for us to find. The WOW, Signal and 3I Atlas, regardless of their ultimate explanations, have contributed to this broader intellectual project by providing concrete examples of the kinds of anomalies we may expect to encounter and the frameworks we need to evaluate them responsibly. They have highlighted both the excitement and the challenges of investigating phenomena that might represent our first brush with extraterrestrial intelligence. At present, we wait in a state of productive uncertainty. We are aware of extraordinary possibilities, but remain grounded in scientific discipline. This delicate balance between openness and skepticism represents one of humanity's greatest intellectual achievements. It allows us to pursue revolutionary discoveries without succumbing to the pitfalls of wishful thinking or confirmation bias. The story of the WOW. Signal and 3I. Atlas ultimately transcends narrow debates about alien intelligence or cometary chemistry. It represents humanity's coming of age as a cosmic civilization. We are moving from passive observers of celestial phenomena to active participants in the search for our place in the universe. We are no longer content simply to catalogue what we see. We now actively listen, probe, and seek signs of other minds among the stars. Whether we are alone in the universe remains one of the most profound questions our species has ever posed. The apparent correlation between a mysterious radio signal and an enigmatic interstellar visitor provides no definitive answers. Yet it offers something equally valuable, a framework for thinking about how answers might eventually emerge. It shows us the kinds of evidence we must be prepared to recognize and the kinds of methodologies required to distinguish extraordinary claims from natural anomalies. In the months ahead, as 3I Atlas continues its passage through our solar system and our instruments continue their vigilant monitoring, we carry with us the accumulated wisdom of generations of astronomers who dared to look up at the night sky and wonder what might be looking back. Their curiosity is our inheritance. Their questions have become our quest. The next wow moment may come tomorrow, next year, or decades from now. It might arrive as a narrow-band radio transmission, an optical flash from a distant star, or the sudden realization that a visitor from interstellar space displays properties that no natural object possibly could. When that moment comes, and the optimist in every scientist believes it will, we will be ready. We have built the instruments, developed the protocols, and cultivated the intellectual frameworks necessary to recognize, verify, and respond to evidence of extraterrestrial intelligence. But readiness is not only technical, it is also emotional and philosophical. What sustains our search is the sense of wonder and possibility that drives all great discoveries. The universe is vast, ancient, and filled with more stars than there are grains of sand on all Earth's beaches. Among those countless suns, the laws of physics and chemistry have had billions of years to create complexity, diversity, and perhaps intelligence. The correlation between the WOW, signal, and 3I, Atlas, whatever its true nature, reminds us that in such a universe, anything is possible, and that the most extraordinary possibilities may be the ones most worth pursuing. As we close this chapter of cosmic investigation, we do so not with final answers but with better questions, not with certainty but with refined methods for engaging with uncertainty, not with conclusions but with the confidence that our species possesses both the tools and the determination to continue seeking truth among the stars. The cosmos keeps its secrets well, but we have proven ourselves to be persistent students. Whether we are alone or accompanied in this vast expanse of space and time, the search itself ennobles us. It challenges us to think beyond the boundaries of our world and connects us to something larger than our individual lives or even our planetary home. In the end, that may be the greatest discovery of all, that we are capable of asking such questions and brave enough to seek their answers wherever they may lead us into the infinite darkness between the stars.